Hello everyone, welcome to our webinar, Future of Cryptographic Engineering. It's our pleasure to host this event. We have world-renowned academicians and scholars in this field. My name is Erkay Savaş. I'm the Dean of Faculty of Engineering and Natural Science of Sabancı University. So we are going to start the event in a couple of minutes. And then I would like to invite Sabancı University President, Professor Yusuf Leblebici, to give the opening remarks. Yusuf Hocam, the floor is yours.
Thank you very much. I'd like to welcome everyone to this very special event. All the participants, colleagues, welcome to this special webinar. On behalf of Sabancı University, we are very excited and honored to host a very high-level group of lecturers in this event. We have put together a very nice and I hope satisfying program for you on the future of cryptographic engineering. Myself also, I have been involved in this field a little bit, and I have to thank especially one of the participants, one of the lecturers today, Professor Christoph Paar, who has introduced me to this field years ago, nearly 25 years ago, when we were back in Massachusetts at that time, and working on different topics. Christoph thankfully introduced me to the wonderful world of cryptographic hardware design. And I became aware of this field, and later on, myself and my students have worked to some extent in this field. And we noticed that cryptographic engineering actually presents very interesting challenges also to us, chip designers, hardware designers. Cryptographic hardware is very special and very challenging. And the solutions that are needed to have successful results in cryptographic engineering require not only performance, but also very innovative solutions that mesh very well with software and algorithms. So in order to design successful cryptographic hardware, you also have to understand the algorithms and the software to a very deep extent. This is the beauty of this field, and I am really excited to see that the field since then, for the past 25 years, has developed above and beyond our wildest expectations, and it is still developing very fast. It has implications all over the world in the life of everybody, and it will continue to be so, even to a greater extent. So with these thoughts, I'd like to welcome the very extraordinary group of lecturers today who will present their lectures. And I give the floor back to Erkay Hocam to introduce the program in the greater detail. And I wish all of you, all the participants, a very nice and fruitful webinar today. Thank you.
Thank you very much, Yusuf Hocam. Thank you very much for this opening remarks. And I would like to thank you once again, because you are the owner of this idea to start this event. What am I going to do? I would like to thank all the speakers also for their contribution, are accepting our invitation to come here and give the talk. So what am I going to do? I'm going to share my screen, and I'm just going to basically give some information about what we are going to talk about today, and I'm just going to introduce the the speakers today. Okay. So the name of the webinar is Future of Cryptographic Engineering. So why cryptography? Because cryptography came to prominence, in recently, because it provides all the tools for cyber security for us. I mean, if you look at this one, more than 90% of the web traffic is encrypted, basically. All banking, financial applications, and the e-commerce applications rely heavily on cryptography for security. So also we have new kind of application that are likely to change the world, you know, the way we know the world, like blockchain applications, and which are not possible without crypto. E-signature, zero-knowledge proofs, you basically start hearing about all these things, homomorphic encryption that allows us to process encrypted data. So all these things are, you know, nice topics. All right, so what is cryptography? When you think about the cryptography is mostly mathematics, okay? And so we have elliptic curve cryptography, we have RSA, we have Diffie-Hellman key exchange protocol, and all the other variants, all right? So what we can just think that these are all mathematical objects. What you can do, you can cryptanalyze them, investigate their security, and you can find out, okay, these are theoretically sound and computationally secure, all right? And then you may just think that, okay, let's, you know, go ahead and implement them in hardware or software. So can we just give it to a kind of hardware, you know, engineer or software developer just to implement it? In fact, the things are not that straightforward, all right? Because implementation is full of challenges. So, and first of all, the mathematics is so involved, and then you have to understand the math correctly. And then afterwards, you have to basically, all these operations are complex and complicated. The implementation could be, I don't know, prohibitively slow. It can be resource consuming. Then you have to think about, well, how can I make it fast? How can I make it small, energy efficient, require less power, or just balance the time and area, or this kind of thing. So these are all implementation details. But what about the secure implementation? Today we are going to talk about secure implementation. So as I said before, the cryptographic algorithm, you can just think like it as a, you know, mathematical objects. It takes certain number of, you know, bits as an input and produce certain number of bits, you know, as an output. So when you come to think of like this, okay, everything is perfect. But what happens in the real world, right? When you just run the cryptographic algorithm on real world, in real devices, so you just have something, you know, like what is called, am I muted? No. All right, okay. So what happens here is that, for example, there are certain things, other kind of information that we can basically observe, like execution time. How long does it take, you know, to run an algorithm, cryptographic algorithm? And it changes from, you know, input to input. So therefore, you can observe it, and you can just, you know, make some predictions about the secret key inside. And we can just look at the power consumption. We can look at the electromagnetic emissions, and we can look at the, you know, microarchitectural artifacts that is happening when you are running your cryptographic algorithms. By observing all this side channel, you can basically infer the secret key inside. And probably you heard of this meltdown attack. It's a really, really, you know, famous attack, or Spectre attack. Basically, you know, with this attack, so they are so powerful, you know, very regular user level, user level application can read the entire memory, which basically collapsing the, you know, the computer, the fundamentals of the foundations of the computer security. And fault attacks, you know, as I said before, cryptographic algorithm just runs in the, you know, in the physical world. What you can interfere, you know, with the cryptographic algorithm execution. As a result, the output may change, and it can produce, you know, the incorrect outputs. But what if, you know, that happens? Well, it happens a lot of things, because we can just infer and, you know, get the cryptographic key, which is embedded inside a cryptographic algorithm. So these are the implementation details. And so, for example, you may heard of this trusted execution environment. You know, in nowadays CPUs, you know, microprocessors, you know, by Intel, ARM, AMD, RISC-V, which is the open source architecture. You know, they are claiming that they are, you know, basically giving some sort of a secure, protected enclave, so that you can run your high security, highly sensitive applications in this. But are those environments, you know, secure? Because we are using cryptography there, we are using hardware there, but are they really, you know, secure? And also, another question is that quantum computers, and IBM is basically making some claims like that, in a couple of years we are going to reach 1,000 qubit, general purpose quantum computers. So what is going to happen if we have quantum computers? What is going to happen to elliptic curve cryptography, RSA cryptography that we are using to secure the internet or secure everything basically? And we are going to basically talk about all these things. So without further ado, I'm just going to stop here. These are the things that we are going to talk today. These are the speakers, and they are world-renowned cryptographers, applied cryptography, cryptographic engineers. So we are really happy to have them here giving us their talks. And I'm just going to basically, introduce them one by one later on. And here's our schedule here. And with this, we are going to start our, our real program in a moment. And then I just want to, start with our first speaker. Our first speaker, let me give you some introductory remarks about Ingrid Verbouwede. Ingrid Verbouwede is a professor of COSIC Research Group of Electrical Engineering Department of KU Leuven in Belgium. Ingrid's main expertise includes system and architecture design, embedded system, ASIC and FPGA design, and design methodologies for real-time, low-power embedded systems, and more specifically, embedded security systems. She is experienced in interdisciplinary research linking design for security with novel technologies and circuits, and investigating the requirements of novel cryptographic algorithms and software security requirements on secure hardware and hardware-software co-design. Her ability to cross the gap between the algorithm and protocol development and actual implementation in hardware, software, and embedded systems has been widely recognized. Ingrid Verbouwede has experience in running small and large research projects, fundamental ones like sponsored by NSF or FWO, basic research funded by EU, and applied in collaboration with industrial partners. Ingrid Verbouwede is a fellow of IEEE and a member of the Royal Academy of Belgium for Sciences and Arts. In 2016, she received an advanced ERC grant, and in 2017, an IEEE Computer Science Society Technical Achievement Award for pioneering contribution to design methodologies for temporal-resistant and secure electronic system. And she's going to give a talk, and the title of the talk is going to be Recent Result with EM Attacks, Passive Observations and Active Perturbation. Ingrid, floor is yours. You can share your screen as you want, and the mic is yours also. Thank you very much for accepting our offer and joining our webinar event. Thank you very much.
Thank you for introducing me. Do you want the video on also maybe? I'll try. It's a pity that we cannot be present all the way in Sabancı. I've never visited the place, but I'm looking forward. It would be nice to visit it. But so now this whole event is virtual. So let's work it virtual. Let me share my slides. Can I share? I guess I can, no? Share screen. Yeah. So my title today, and you actually gave a very nice introduction about all the topics which are hardware security or very important or hot topics, and like microarchitectural attack, side channel attack, crypto that is post-quantum secure but should still resist side channel attacks, and so on. And I picked one topic. I looked at the other presentations and I picked one topic. And one topic that I took is actually electromagnetic attacks. So it's one category, and electromagnetic attacks, how you can do this actually remotely, because in the IoT context, this might be an issue. Next slide. How do I go? Okay. So this is the outline of my presentation. So first I'll introduce a little bit what I mean with IoT, or Internet of Things security, and the fact that composition kills there. I'll give a short overview. Since I don't know what is your background on what we mean with fault attacks, and specifically with electromagnetic fault attacks and EM fault injections, and I give some example. So you probably all have seen similar announcements as this slide. We are surrounded with secure embedded devices, or devices that should be secure. This is now a couple of years old, but basically hackers could remotely, they don't need to be in the car, kill a Jeep on the highway and just drove off with the Jeep and drove it into the site. Now this particular one didn't have too much of damage to the people that were sitting in the car, but it was hugely economical damage, in the sense that Chrysler had to recall more than 1.4 million vehicles just to fix the bugs in the embedded, actually in the security of this design. And it was a problem with actually the internal card network, or the CAN network, being exposed through the media network. You see other things. Another example I have here of an embedded device is maybe a defibrillator. And important to note is that, for instance, I know of only one person whose pacemaker was modified to prevent hacking, and that was Dick Cheney. He was a former vice president in the US. There is many more attacks that you see on these things, and what I think which is unfair is that his pacemaker got protection while most people just don't, because pacemakers are programmable devices, and they are connected to the internet often, so that doctors can monitor how the patient behaves, say, outside of the hospital, in its normal environment, and so on. So we have seen applications where pacemakers could be tuned to the patient even from a distance. But if you can tune the pacemaker, you can probably also adjust it in the wrong direction. So what is actually the problem with IoT security? And the problem is that composition kills. Before there was the Internet of Things, there were just things. And one example, which I took here from Aurélien from Francillon, is that people would put cameras on their driveway. And they put a camera on their driveway just to monitor who would come and ring the door. And the little monitor and the screen was somewhere inside the house. And this was supposed to be sold for video protection or video surveillance. And up to you how to interpret this. Now, the tendency or the evolution is that this camera is no longer just locally, but no, now there is a wireless link to it, Wi-Fi, it goes over the cloud, and all of these devices now come with an app on your phone, which then you can monitor who's in your house. Now, this original little camera was never built with security in mind. So what happens is that people in France, because this was a French study, figured out that with all these cameras, you could simply watch in everybody's bedrooms all over France. This was a really big problem at that time. Maybe now it's fixed, but basically what is the problem? It's composition. The camera by itself is probably okay. The app by itself is okay, but now connecting this to the internet is that the composition actually makes it a security hazard. And it only gets worse. I think this is a really cool cartoon. I don't have time to go through all of them, but this is a cartoon which says that all these little devices, they will be connected and they can actually now start to charge ransomware. And this is not just fake, this is also true. We have done some experiments here on, say, rice cookers or coffee machines, which actually, the nice thing is you could program them from your app, but the disadvantage is that all that data went somewhere to a server in China. We want to avoid that, right? So the fundamental problem is that by connecting this camera to the internet, now the attack surface has increased. And devices which originally were not designed for security, they now go online. So the threat model has changed, and we have to take that into account. And the value of this device just increased by being online. So the protection has to go with it. On top of that, many of these devices are just deployed and afterwards they're forgotten. So now this is the big context or the big problem. In this presentation, I only want to look at what the non-invasive remote fault attacks as part of this whole problem. The nice thing about EM, or at least remote EM attacks, is that it's kind of remote in the sense you don't have to be close to your electronics. Maybe you can observe over the power cables 1 meter, next door, next room, and so on. So the electromagnetic attack kind of fits in this thing, and I would like to show you a couple of experiments we're doing now or working on. Some of it is still work in progress on what you can do with electromagnetic attacks. Let me first introduce a little bit what I mean with fault attacks. We got already a little bit of introduction by the chair. So fault attacks are actually active attacks. They're active attacks in the sense that you, from outside, try to trigger a fault or a misbehavior. Now, faults can occur in software and hardware. We have learned in our electronic classes, you might have alpha particle injections, things like that. You can have some degradation because of other events, but they're just random, often just random. They can cause errors, but if we do it intensively, these errors maybe can be exploited to expose secrets. There have been some very famous examples of the RSA encryption algorithm, where if you first calculate without injecting a fault and then calculate with a fault, but only one fault, you could break the whole key. So these fault attacks are different, but kind of related to testing for reliability. They're also different, but kind of related to EMI, electromagnetic interference testing. And then once we know what is a fault attack, we want to know what fault models exist. Often people look on what do I attack? Is it how many bits are affected? Can I do single bit, few bits, whole word, whole region without having too much granularity? For those that have followed classes on faults, you know you can have stuck at 1 fault, stuck at 0 faults, you can have flip bits, random faults, things like that. We also kind of check them on how precise the fault location has to be, the precision, and on the timing, a particular clock cycle or just a whole period, and the duration or the effect of the faults. You can have transient faults, you can have permanent faults, but you can also have destructive faults. Transient faults are often the ones which are most difficult to detect. I'll give you an example of a transient fault later. And then how the attacks, whether they're invasive, semi-invasive, non-invasive. Non-invasive are those attacks which do no physical damage to the device. Maybe you modify the working conditions. Maybe just by heating up or having a high temperature, you can break some things. So these attacks are often very cheap to set up. You only need moderate knowledge, cheaper equipment. Semi-invasive are chips like maybe attacks, maybe you have to do some chip decapsulation, but not more than that. Milling, etching, cleaning, and this is still affordable equipment. This is students have often access to it and so on. And then you might have really invasive attacks. You need more advanced equipment. Maybe you have to make electrical contact to the chip. Might be even with expensive equipment, say a fib or a laser, but some lasers these days are also cheap. I've seen fault attacks, I think by Sergei Skoborovatov at some point, where actually the flash of a camera was used to inject faults. And then there is many fault injection methods. You can play with voltage glitching. You can play with clock glitching. Voltage glitching, there has been a recent attack in the category of micro-architectural side channel attacks using performance counters on the chip. Performance counters, as you know, are internal counters that monitor how well your CPU is doing. Playing with those performance counters and voltage glitching, you can attack clock glitching, playing with temperature, EM fault injection, optical faults, and so on. So here you see a laser injection. This is a picture of one of our EM injections. So I'm going to give you now two examples, one from one PhD student on the creation on how do you create now EM pulse and what could be the effect, and the other one of EM frequency injection. So fault injection. So an important thing is fault injection. If you have an integrated circuit and you want to inject a particular fault with EM, so that's non-invasive, you actually want to inject an EM pulse, and the EM pulse is going to couple with all the wires on your chip, the bounding wires. So, and what you will create is probably some pulse internally, or either a voltage current pulse, which might damage or which might change the setting of your device. For instance, we have done some experiments. I've seen that non-volatile memory is very sensitive to EM injection, because you're injecting charge, and the charge on your non-volatile capacitances might change. Now, how do you make such a probe? There might not be. There are some custom probes you can buy. For instance, they are being sold in the context of EMI, electromagnetic interference, where they're being used. Here we did experiments with both off-the-shelf pulses, but also built our own pulse injections. And pulse injection is actually an RLC circuit. There is a resistance value, an inductive value, a capacitive value. And depending on actually the damping factors, you can create different kind of pulses with a different, in time, and with a different in distance from like the center point. And these are some experiments for characterizing some probes. This was the work from Arthur. And depending on the size of the capacitance, it will change a different pulse over a different time frame. For instance, a large capacitance can give you a high peak, but maybe the timing is too slow. If you want some small, narrow peaks, or certain, if you only focus one clock cycle or one period or something like that. The number of windings is an important factor, which you see here, from 2 to 10 windings, and you see the more windings, the longer the pulse will be. 2 windings is much more sharper pulse. The core diameter, not that much difference, and the material, whether you do the type of ferrite material in the cytocore doesn't differ that much. And then we did some experiments, and you can see our test board here, and the test board sits on top of a typical demonstrator board. Is an ST microcontroller. An ST microcontroller that runs Cortex-M4 runs, say, on 100 megahertz. It's not decapsulated, so it's just a standard microcode. And this, we put some code in there, and we see, or we try to see what we can influence. And this was, for instance, to demonstrate impact of the pulse shape. Can we attack individual registers, or it's just larger region, or what can we do with this pulse generator? And this is one of these results. And you see here, this was a critically damped probe. So this is the pulse that the microcontroller will see. And this is an underdamped probe. So you see much more of a ringing. And these are, this is the time, and these are the registers that are being affected. Now, so time goes from top to bottom, and these registers are actually sequentially accessed. That's why register 9 is later, but you can see that you can attack individual, or you can modify the contents of individual registers inside this microcontroller with this particular pulse, because it's narrow enough. Now with this ringing type of pulse, you see that not just one, but multiple registers were addressed. So you can play with the probe there, depending on what you need. I have a second example, and that's actually, instead of a pulse, we're now going to inject a particular frequency. And this, people keep on saying, yeah, with EM, you can inject frequency, you can actually modify through random number generators, but not much actual demonstrations have been shown. So as you know, random number generators are essential building blocks. They're essential building blocks in cryptographic protocols. Crypto people rely on it for freshness, people rely on it to generate keys, for instance, some countermeasures based on masking. They use it to use fresh marks and so on. So there's many places that a random number generator is used. And if you can break the random number generator, often the security protocol will fall apart. Here's an example of that. This is I got it from some publication. This is Taiwan Citizen Digital Certificate. And the goal there is to give some public key infrastructure where you could sign documents, things like that. Now, just by watching to the numbers that this thing is generated, already you can notice that there are problems with the random number generator, right? So the amount of entropy you get out of this sequence of numbers is way smaller than what you expect from a true random number generator. And that was because there were some flaws in this design. So what we want to do with this EM is, we call it intentional electromagnetic injection. That's the work from Osaka, new PhD student. And so we know that if we have a random number generator from close by, we can inject maybe frequencies and get some effects. But here we want to inject from a distance. And basically what we're gonna do, we're gonna inject through the power cables, because the power is connected to the device. And so you could inject one frequency, and you could see here, for instance, that the bit stream that's generated with this onboard random number generator, that it's clearly reduced, so that the entropy is clearly reduced. Maybe some other frequency comes out and it's not reduced, so this is the wrong frequency. This is how it will. So what are basic structures of random number generators? So you have here you typically have a set of ring oscillators. We have many circuits people here, I assume. These ring oscillators have different lengths, and in the best case, they actually, you try to make them co-prime to each other, you XOR them together, and you sample at some frequency. And if the randomness comes from the fact that these ring oscillators have jitter, and the jitter is fundamental, is the entropy that you're trying to harvest. So a normal TRNG output will look like something like this, but if you inject, then you try to get these ring oscillators in some locked state. You can clearly see the reduction in randomness. So the experiment we did, or that Saki did, is actually two ring oscillators. One was an 11 elements, the other one was 9 elements, connected to some device. And then this is typically set up. What's important to see here is that actually we're trying to inject frequency from a probe injection probe on the power supply line. And then if this is like implemented, so these were some ring oscillator implemented, you extract the entropy, maybe you go to some logic analyzer, measure the ring oscillator's outputs, and then you have a second probe, the current probe, that actually goes through an oscilloscope, and you do actually a frequency analysis. If you have a true random number generator, then you're gonna have a frequency spectrum is gonna be all over the place. If you have some locking or reduced entropy, you can notice that on the frequency, because then you only a small set of frequencies will pop up in your frequency analysis. So this is the setup. So yeah, this is what you pick up then from the logic analyzer for the bit stream. So if you inject a frequency which does not create any problem, so you have, so this is the scope which is locked on one frequency, and you see the other one is just random around it. And if you look at the frequency spectrum, then you see you have frequencies all over the place. If you inject at the frequency that makes them kind of lock or align, then you see that the number of peaks gradually reduces. That's how we monitor. That's how we monitor the quality of the ring oscillators actually, and the quality of the entropy. So, and then these are some experiments of what's happening at different frequencies for this particular case. And you see this is at 18.5 or 27.2 or 91.4. And you see all of them have like a nice distribution of the frequencies. And if you do NIST tests on it, the p-values which are calculated are low enough, so you don't have high enough, so you don't have any problem. Low randomness, you see some examples here. These are frequencies at 58.3. You get this kind of pattern. At 78.1, you get this kind of pattern. At 90.3, you get this kind of pattern. So these are clearly frequencies that influence the onboard ring oscillators, and we should try to either avoid them, or yeah, the problem is this is now injected from a distance. How can you onboard on your chip avoid that this is happening? Now, this is a big deal in designing random number generators, and there are standards for it. The German BSI has some quality standards, and it's called AS31. NIST has some standards which were recently updated, SP 800B and C. Now, if you design a random number generator according to those standards, you have to provide all the blocks on the screen. So you're gonna have a digital noise source, and in our case, that's, for instance, the ring oscillators, but you also have to foresee on your integrated circuit modules which are called total failure tests, online health tests, and some post-processing. Post-processing is there to say, for instance, you have maybe high-quality numbers, but there is bias in the numbers. The post-processing might be some algorithmic techniques to reduce the bias in the circuits. For instance, XORing bits together, or von Neumann post-processing, things like that. The important block that I want to point out here is the online health test. You have to provide tests that, while the random number generator is working, kind of monitor the numbers that are passing by. So you would like to have a test that monitors that your randomness is degrading, like here, right? So here is probably a problem with correlation, because if you have, you can clearly predict what's going to be the next bit if you know one bit. So these online health tests. Now, for these online health tests, we have quite some options. You can use hardware or software that implements the statistical test from the standards. You also have to provide for a random number generator that you want to be certified or having an AS31 stamp. You have to provide a stochastic model. So what's this jitter model, physical models, things like that, metastability and so on. Or you could include what's called source-specific tests. The big challenge is there that you can do quality statistical tests if you accumulate a lot of numbers. Now, on a small embedded device, on a pacemaker, we don't have room, we don't have megabytes to collect all our random numbers and then release them as we need them. No, you have to be able to generate a judgment while the numbers are processing by. So you want an online health test, that's a security challenge, that's low latency, so that quickly decides, but not having maybe a lot of numbers. The second question you have to ask yourself, can I release the data or the numbers that are generated by my random number generator before it has been checked, before they get the check? The random number generators of Intel, for instance, they come with a health bit. But an Intel processor, there is room. You have room to store megabits if needed, right, of bits before you release. And with many of these embedded devices, you don't have that. So you have to check what is the memory requirement. So this is a latency issue and a memory requirement issue. And so one option is that you add source-specific tests. So you try to figure out what happens if I apply attack X. For instance, if I heat it up, what happens if I heat it up or I cool it down? Many circuits are sensitive to extremely low temperatures, because with low temperatures, you don't have as much jitter. Or what happens if I do clock glitching, oversampling, things like that. So you can add source-specific tests. Now for these EM remote attacks, this is kind of difficult because it's difficult to figure out that you're under attack. How do you know? How does the little circuit knows that there is an attack happening? There's no temperature sensors or EM sensor. And the second thing is actually it's transient. You can turn it on and off. So yeah, this is a work that we've done in the past on how to design some of these online source-specific tests, the tests which are tailored for the specific source and for the attacks that you might expect. Now here you see an example of what happens if I do an EM injection, possibly remotely, but I turn it on and off. So here this injection frequency is being on and off. So here was, you applied for 500 milliseconds, for 300 milliseconds, for 100 milliseconds. So if you apply it for a long time, your online health test probably can detect that is an issue here, that there is a problem here. But if you make the window smaller, it might still pass, right? So this is at this moment, we haven't solved this, what is a good balance. Because you don't want to raise too many false alarms neither. So the attacker tries to stay actually below the detection radar by manipulating actually injection window. So I've given you like 2 examples. I only have a half hour, 1 minute left, I think. I want to connecting things to create the Internet of Things is a huge challenge. I completely agree with the president and the chancellors that gave you an introduction. And this is still the start. I think there's so many things we can do. So in this presentation, I was only focusing on electromagnetic attacks, remotely non-invasive, and they're especially interesting from an attack viewpoint if they're transient. And so I've shown you that we've done some work on injection probes, study on the effect on random numbers, the health tests. But there are, in my opinion, many more interesting topics in embedded security, and there is a clear future for what you call cryptographic engineering. And I just received, after things, a new ERC grant, which I want to look at some of these topics that will be also discussed today. And if you want to have more information on that, you can ask me. I call it Belfort. And it's about hardware acceleration for computing unencrypted data. So it's homomorphic encryption on FPGA in the cloud, which all the topics which are discussed today probably will bring together. And that's the end of my presentation. I don't know what is the procedure.
Yeah, thank you very much, Ingrid. That's really, really. Can you hear me, by the way, Ingrid?
Yeah,
thank you very
I
much.
can hear you very
well. I mean, I really like to thank you. I mean, it's really, really great pleasure and honor to have you here. That was a very, very interesting, talk. Thank you very much. And I'm glad that you are working in the same topic as we are, like homomorphic encryption. This is really nice. Anyway, so what we can do right now, the procedure is the following, and then the audience, I mean, the participant can, write down their, question is the Q&A part, and we are going to, read them to you. And you can see the, Q&A box yourself, but I have here with me Erdinç Öztürk, probably you know him. He's going to help me a little bit. So we have a bunch of, questions in the, Q&A box. Do you think we should read it to you, or?
I can read them.
So just pick anyone you want to answer. That's up to you, Ingrid. Thank you.
Yeah, I'm fine. I don't know how strict you are about the timing. So I could say one is standardized test for IoT security. I think people are working on that, but that's really a tough one. It's so broad that what is IoT and starts already there. For specific domains, there are standards. For instance, smart card business, common criteria, things like that, but these are expensive. Then the effect of very short pulses, terahertz per photo mixers. Might be cool. Haven't tried it. The question is, with these pulses, can you also inject energy? Because it's not the pulse itself, it's also I have to have enough energy injected there, right? And then the last question is about the distance. Yes, this experiment is about 0.5 meter to 1 meter that we do on the EM cables. But I have seen in the past EM that goes actually, this was on some screen sets, and that would just enough that would go through the walls. And so you're in a cubicle system, and you have a distance that goes through the walls, and actually you could monitor what your neighbors are doing. That's kind of. Can lattice cryptography be used in IoT usage? Yes, I'm convinced of that. We are very proud in Leuven that one of the well-known, one of our algorithms is called Saber. Saber is a post-quantum candidate for the NIST competition. It's lattice-based, and I'm sure that many people here know what is the Saber algorithm. It's post-quantum based, and we're actually working on getting it on small embedded microcontrollers, so as can also try to make some implementations. Yeah, I think we can keep going.
There are a lot of questions here. Well, I don't know. Maybe you can answer one more question, and then we should stop there, Ingrid. If you feel like.
For students, if you like to start with an EM attack setup, there are some. I don't have to turn this off. There are some development boards that you probably can buy and start from there. There are also some basic EM probes you can buy, and you typically go by the EM probes which are used for EMI, but that's already quite expensive. These EMI probes are quite expensive. You should start. Yeah, with simpler things. Okay.
Yeah, Ingrid, thank you very much. Yes, there are a lot of questions. People would like to ask a lot of questions once we get you, but we have to stop somewhere. Thank you very much. I really appreciate. So coming, and giving this exciting talk for us. Thank you very much, Ingrid. Thank you.
You're welcome.
Thank you, Ingrid.
All right. So maybe we can move on to the next speaker, and Thomas Eisenbart. And thank you very much, Thomas, for accepting our invitation here. Before you start, I just want to read your short bio, if you are there. Meanwhile, you can go ahead, try to share your screen if I know you are there. All right, Thomas, yeah, all right, thank you, Thomas. Thomas Eisenbart is a professor for IT security at University of Lübeck. He received his PhD in electrical and computer engineering from Ruhr University, Bochum, Germany, where he worked as a member of the Horst Gerst Institute for IT Security. From 2010, he spent 2 years at the Center for Cryptology and Information Security at Florida Atlantic University. In 2012, he joined the Electrical and Computer Engineering Department at WPI. Since August of 2017, he is the director of the Institute for IT Security at the University of Lübeck. His research interests are in applied cryptography, system security, and secure computer architecture, side channel analysis, physical attacks and their prevention, cloud and virtualization security. The title of his talk is going to be Isolated Execution Environments as a Building Block for Secure System. As we did before, the audience, the participant can write down their questions in the Q&A box, and we are going to address them at the end of the talk. Thomas, floor is yours, please.
Thank you, Erkay. Just needed a second to find the unmute button. And so thank you, Yusuf and Erkay, for the invitation. Of course, it's a pleasure to be here today. Before we get started, just a short disclaimer. Let me see that I have my slides under control here. Yes. So this is the results you will see are at least the parts that are coming from our lab are joint work with members from the team, such as Luca, Jan, Tore, Berg, and collaborators such as Berg, Florian, Matthias, Daniel, and others as well. So a short overview, what I would like to talk about today is the goal is seeing how we can achieve system security, basically in protecting components that we use for computation. Ingrid already gave a very nice motivation for IoT, and IoT is basically the interaction of many components, and then we have components that have less power, and we have also cloud systems somewhere, and all of these need protection, and they tend to become more complex. One technology that can help us with protecting there is trusted execution environments. We will look a little closer at those current attacks on existing trusted execution environments and how we hopefully can build more secure systems and trusted execution environments in the future. So to build secure systems, we can look at how systems work nowadays. Usually everything is running on some piece of hardware. When a system boots up, it's usually booted up by the BIOS. Then an operating system is launched that then will dynamically launch new applications as needed. These often require shared libraries as well to operate. So it's kind of a pyramid, if you want, with different layers, and each layer depends on the layers below, and especially the operating system has a very important role here because it is the place where usually security policies are enforced, which should protect apps from each other, for example, separate them and things like that. But basically, whenever we have a problem at one of the lower layers, then security assumptions we have for the higher layers are basically broken. So systems can be compromised. And as we go into the future, as systems evolve, the size of this pyramid tends to grow, so systems are becoming increasingly complex. And one area where this is happening is cloud computing. Another area is also embedded systems, especially cars, for example, are by themselves are increasingly complex systems. We have many core systems, both in the cloud, they are very much so, where different tenants rent computation time on the same hardware. But even in embedded systems, we have a similar scenario. So we have many applications that run on the same platform, that share the same hardware. and that have different security assumptions. In the automotive environment, for example, you often have safety critical systems now running next to, let's say, user provided code, entertainment system or something like that. And to still ensure security at this level, we basically one thing that was introduced is a hypervisor. So we want an additional layer between the hardware and the operating system. This layer can provide both horizontal separation between different operating systems or groups of apps, and then of course also vertical isolation to protect hardware and I/O resources from the higher layers, basically. Still, if you have a compromise anywhere at the lower layers, the higher layers become attackable. So hypervisor can attack any layer above, and so can the operating system for the applications within its domain, right? So that's a problem. There is some improvement with the hypervisor. We reduced the trusted computing base a little bit, but not too far. One other approach to increase security of components in this environment are trusted execution environments. So the idea basically is that we allow the execution of a secure process or part of a process independent of the security of the OS or hypervisor. So we basically try to remove hypervisor or OS from the trusted computing base, and this is typically done by blocking these attacks that we saw before, by adding something to the hardware. And the hardware basically ensures that the data and code and execution of code of these little software components, we will call them enclaves in this talk, are actually protected from the rest of the system, so that these attacks are no longer possible. And now you can actually execute code securely on a higher layer, even if one of the lower layers is compromised. You still, of course, have some trusted computing base, and definitely you need to trust the hardware in this case, right? In industry, there are basically three flavors that are quite popular at the moment. Others are there as well. There are also a lot of nice academic proposals. But yes, I will mostly focus on those three mentioned here. So the software components that are executed and protected by the hardware are usually called enclaves. This is the protected code that can run at any of the layers, basically. And to protect them from the rest of the system, we usually use two technologies. One is isolation, the other one is attestation. So isolation, we protect the code and data of an enclave. Usually this is either done by cryptographic means. So we have often the data encrypted and often also integrity protected, or we simply do it by logical means, so that the hardware stops access and prevents accesses from other system resources to access the data of such an enclave. The other mechanism is attestation. Attestation basically deals with the problem of communicating with such an enclave. The enclave is at a higher level, so its execution is completely controlled by the potentially compromised operating system. So communication always needs to go through the operating system. To make sure that there is actually the correct enclave running, we need some form of verification. So usually, when an enclave is loaded, it is measured by the hardware that it is loaded through the code, and potentially data are measured by the hardware, and then the hardware attests towards a third party that this is actually correctly loaded. So there's basically this communication problem is solved as well, so that we actually know that a valid enclave has been started on such a system. So two technologies that are important to actually ensure that the trusted execution environment works. In industry, we see three types of, I mentioned that before, three types of, there are three deployed right now, three types of trusted execution environments. The first one was ARM Trust Zone, which was already deployed more than 15 years ago, popular in mobile phones, for example, that basically splits the software world into two domains, the secure and the insecure domain. Also has hardware support for this, of course, so it basically just two worlds. With Intel SGX, this is a relatively newer edition. The last 5 to 8 years it has been around. Where we can protect processes or parts of processes at the highest level, so in user level processes can be protected, and there can be big difference here is that there is cryptographic protection of code and data, both encryption as well as integrity protection, and that there can be many enclaves in the same system. That's actually baked deep into the architecture of SGX, as the attestation mechanism, for example, builds on an Intel-provided enclave. So basically one enclave measuring the other enclaves together with the support of the hardware, of course. And this is strictly in the user land. And then there is AMD SEV, also a fairly recent addition. So AMD directly tried to protect entire operating systems. So it basically is kind of, for maybe the cloud computing scenario and intended for that area. So we have guest operating systems that can be fully encrypted. So we also have the memory encryption here. We have the attestation mechanism through a secure processor component on the AMD processor. And so the difference compared to SGX is that it's for entire operating systems, protecting them from access from the hypervisor, which is a scenario which, especially in cloud computing, is of course of high interest. And we'll see in a moment, they just launched a new version of that. And Intel is also about to launch such a solution. And there's a lot going on. So let's take a look back what happened in the last few years. So there was a lot of research on analyzing the security of trusted execution environment. And most of this focused on SGX as a new technology that had a lot of promise with sound cryptographic integrity protection and encryption and many other components baked in, which look very promising. At the same time, from a academic perspective or from a vulnerability research perspective, SGX looks also at trusted execution environments in general look very promising, because you need to protect against a very powerful adversary, right? So you're protecting against attacks at the OS or hypervisor level. So basically the attacker controls the entire system and now tries to glean information from a little piece of code that is running in the user level, basically, right? With additional protection, but anyways. So we have a very powerful adversary, and then we can look at what kind of attacks were found. So the first attacks already published in 2015 was control channel attacks. So basically, they used the capability of the operating system to monitor the execution in a trusted execution environment. And the example I would like to show here, it's actually taken from their presentation, is what they did is they basically monitored the decoding of a JPEG image. This is the image, this is an example image, basically birds. The image is being decoded in an SGX environment. So in theory, you think you have a secure code execution there, nothing can go wrong, but you can monitor basically the page accesses. That's what they did here. And what remains is the picture you see here at the bottom. So as one can easily see, there is still a lot of information. There's basically, it's not the same quality anymore, but you can still learn a lot by just monitoring page accesses. That was the first attack. And then in the following years, a lot of attacks followed. A single stepping attack from Bulk and from Bulk and others. There were several side channel attacks, so basically micro-architectural attacks using branch shadowing or cache attacks. And these attacks work very well in the SGX scenario because of the powerful adversarial scenario, right? So because the the attacker controls the operating system, you can basically single step, that's a attack mentioned here as well, single step through such an enclave. You basically interrupt it all the time. You take, you monitor the shared components such as caches, branch prediction units, and so on, and you get a very fine-grained information from these shared resources, and that makes an attacker very, very powerful. Of course, there are methods to make those attacks hard, and we will talk about that later. But yeah. Then there is the in 2018. We had the transient execution attacks, so Spectral Meltdown were published, and it didn't take much time to show that this meltdown-like attacks also work on trusted execution environments. In the case of SGX, that one could actually extract information directly from, that's a foreshadow attack, directly from the trusted execution environments. So I would like, so we see there's a lot of attacks, and I would like to look a little bit closer at AMD SEV, which was not researched as much yet. There has been quite a bit of work as well. As we saw before, this protects at the hypervisor level, or from attacks from at the hypervisor level. There are 3 versions of AMD SEV that have been released. The first one, exactly what I mentioned. The second version improved the interface between the protected operating system and the hypervisor, so basically encrypted interfaces to prevent certain attacks. And now the newest version, which has just been launched, actually changed the attestation mechanism and also added write protection for memory pages of the guest virtual machine. So I would like to first present an attack on the attestation. So we'll look at both the isolation as well as the attestation. Let's start with the attestation mechanism. So what typically happens is when the hypervisor launches a new operating system and wants to launch it in this secure mode, first the boot code is loaded. That code is then measured by the secure processor, by the root of trust, basically. And as code can be quite big, of course, it's usually loaded in chunks. So the hypervisor provides the code to the secure processor in chunks. And so there's still quite a bit of control. And once the entire code is loaded, it's being encrypted by the root of trust. And once everything is loaded, then the execution is passed into this secure operating system and basically boots up in protected memory. So this is quite a critical step, of course. The secure processor measures everything. It is preparing for the boot. And then basically can be involved in the attestation in the end. So it basically can attest what it booted up in the end. So what we saw is that there is a little problem with the way the code is measured. So basically the code is loaded in the smallest chunks you can choose. It's actually 16-byte chunks. And what you can actually do is reorder the way the code is loaded into this into the protected area, into this secure virtual machine, and without changing the hash fingerprint, so without changing the attestation, basically. So just to visualize that, we have 2 code pages, A and B, and usually we pass them one by one to the secure processor, which then in place encrypts them and extends the hash of the hash fingerprint of the image you just loaded into this virtual machine. So what we can do is we basically just change, we keep the same data, but we change the positioning in memory, yet we still call the, pass it to the secure processor in the same order as we did before, just with different addresses. And then the secure processor encrypts it in place as it did before and updates the hash state as before. So in both cases, we get the same hash image. So we get the same measurement of the code, even though the code that we actually placed in the virtual machine is different. It has the same components, but the components are reordered. So this can be done at a granularity of 16 bytes, and that actually means you get quite a bit of freedom of rewriting your code in a way that you can actually exploit it. So how do we do that? We reorder the code of the initial VM image that we control, because we assume hypervisor control. And basically, we need to build a malicious code gadget that allows us to basically change the launch of the virtual machine in such a way that we can get control over it. So how do we do that? All we can do is we can control a few blocks. And what we did is a technique where we reorder based on 16-byte blocks. And what we usually do is, since we have little control over the entire content, we try to find blocks that basically where most of the data doesn't matter, but we only need maybe 2 bytes per block. That is quite easy to find. And we connect these so we always have a jump to the from the beginning. We jump over several bytes that we do not want to control to the end of the next block. Then that is executed. Then the subsequent instruction is again a jump, and so on. So we basically connect many small pieces of code, which we can then, by placing them in the right order, we can control the connection. So we are building a chain of blocks. If you want to have fun, you call it a blockchain. I like that. My students are always a bit scared of that term. And by that, you can actually achieve arbitrary code execution. What we do in this stage is basically just rerouting which code is being executed to a public page, and then we can place whatever we want to do there. The measurement still succeeds because the blocks are still the original code that of the original virtual machine, just loaded into memory in a different order, and then the effect when you actually execute the code is different. So so basically with this problem, you can bypass the attestation and then do whatever you want. So as an example, in this work, we extracted a hard disk encryption key, because the memory encryption that SEV provides is only a part of the solution. You're blocking the hypervisor, but if you want trusted execution or trusted computing in the cloud, you might also want to read from persistent storage, for example. For that, you would use classical hard disk encryption, and then the key, of course, needs to be stored in the VM image, and you could easily extract that with this attack. Then the second attack targets the encryption modes, and so we are looking at attacking the isolation mechanism. So memory in SEV is encrypted, but it's not integrity protected. And so that's actually quite interesting, because the operator and the hypervisor can still move data around. Basically has control over the pages and can also move around data. So maybe that reminds you of the previous attack. We'll see something similar here in a moment as well. So one can move and replace data in the guest memory, and without integrity protection, of course, this is maybe not such a good idea. However, the assumption was that the attacker has no idea what the resulting plaintext is if you just place something in the ciphertext. However, they're using XOR encrypt, so tweakable block cipher design, basically. But what is noteworthy is that the tweak is predictable, because it is only address dependent. So you have the plaintext, you have a key, of course, in the AES, but the tweak itself depends only on the address. And at least in the earlier versions of SEV and SEVES, you were able to predict the outcome of the tweak. So how do we exploit this missing integrity check? So there were several works that used I/O control. So the hypervisor controls I/O devices. The guest virtual machines also need, of course, I/O access to communicate with the outside world. So that communication goes through the hypervisor. That means the attacker has control over the I/O, and even though your memory is entirely encrypted, moving data into the encrypted memory and out of the encrypted memory is necessary when you want to use I/O, such as networks, such as hard disk communication. So you definitely need that. And basically, there's different ways of doing this, but what you do is you use the fact that data is first placed on on an unencrypted page is then, that data is then being encrypted to enter the virtual machine. So you can place you can place chosen plaintexts, and this is then being encrypted into the virtual machine. So you basically have an encryption oracle, and the same if you manipulate the way data leaves the enclave or the secure operating system, then you have a decryption oracle basically. And there's two ways of doing that. Either you directly move data, again, you can do that in 16-byte chunks, or depending, you can also use the hypervisor's power of messing with nested page tables, and then you're just swapping pages directly, right? So with that, you can either leak secrets or you place executable code. We try to do this without I/O access, and under the assumption that you have some known plaintext ciphertext pairs already in the protected virtual machine. And that can, for example, be the boot code, which is usually placed in the memory in a contiguous fashion. So it's one blob that is placed in contiguous memory. It's typically a few megabytes of code. And with that amount of known, and there's only a few versions usually for an operating system for this boot code. So you can assume this to be known. And with knowledge about that plaintext, you can then you have a known plaintext ciphertext pairs. If you move them around, you can again do things like to get arbitrary code execution. So you can do the same thing we did before by chaining again together certain blocks, or just doing an injection attack. A simple example here. So we take our code, we place it at a certain location, and then the code just executes. An example is a password check. So here we have a code that performs a check whether the passwords are the same, and then does a conditional jump either to continue, that's a green arrow here, or do an abort code, that is this area here. And the blocks you see here, the black lines, basically this is what is highlighted in red, is one block that is encrypted on its, that's one encryption block that you can exchange with a different encryption, with a different ciphertext. And all we need to do now is we need to find a ciphertext that decrypts so that we have control over 2 bytes in this example, right? So that we have no longer a conditional jump when the test succeeded, but that we always jump to continue, that the code continues as if we had entered the correct password. So these kinds of checks you can directly manipulate by placing the ciphertext, and because you can predict the outcome of the plaintext or the outcome of the decryption for a known plaintext ciphertext pair, you basically just need to search through all the ones you know and to find one that decrypts to exactly this pattern. And with 2-3 megabytes of known plaintext ciphertext, that's actually quite easy. Again, we can use the same technique that we saw before, this block chaining. So because again, all we need is about 2 to 3 bytes per 16-byte block to be predictable, to build a chain that we can actually execute then, and basically to take over control of the execution flow and then execute arbitrary code. So what do we see here from what are our lessons learned from looking at trusted execution attacks on trusted execution environments? One needs to check whether the security policy is consistent. AMD in this example opted to leave out cryptographic integrity protection. That can actually work, but you need to ensure that integrity is ensured by other means, if not cryptographically. Cryptographic integrity protection adds a lot of overhead, so they wanted to avoid that. Then you need to do something else. The other one is the one that we saw on SGX specifically is that we often do not have protection against side channel attacks. Well, that is also, it's a design choice, but then you need to make sure that your enclaves also are protected against these kinds of attacks. So SEV SMP, the newest generation that just came out, added a lot of protection, integrity protection, without adding cryptographic integrity protection, by making sure that the physical placement of pages cannot be changed by the hypervisor anymore. Once they are placed once and they cannot be moved anymore, and the hypervisor also no longer has write access to those pages. They also exchanged the attestation mechanism that this reordering is no longer possible, because now they actually have fixed virtual to physical page mappings due to the prevention of reordering of the pages, and they also use bigger chunks now, so the attacker presented this basically in the newest version is actually prevented. However, that doesn't do anything with the side channels. So many of the attacks on caches and control channels and so on, they are still open. So I hope I'm still okay on time. I'm almost through. So what can you do about that? Well, you can, of course, try to give your developers tools that allow them to ensure that there is no side channel leakage in the code they write. And one important component is constant time code or data oblivious code. It's kind of the same thing. So you want your code to the execution flow and memory accesses to be independent of any secrets. And there are several tools, static and dynamic analysis tools. We looked into dynamic analysis. We actually built a tool a few years back that uses dynamic instrumentation, and we used it to analyze closed source libraries, Intel Pin and Microsoft CNG, and found a few issues. Yeah, basically many of those issues have been fixed in the meantime. So you always need to generate test cases, then the code is actually executed if you follow this dynamic analysis approach. Basically what you get in the end is execution traces, which you then compare to each other to see if anything happens. So that is a way to verify that, at least experimentally verify that your code does not have any secret branches or memory accesses anymore, so that it is actually does not leak through the attacks that we just saw. Similar things are also possible on the hardware side. So I just want to highlight one work here that use a model checking approach to verify that the hardware design doesn't have such transient execution bugs, which we know from meltdown-like behavior anymore, so that the behavior under transient execution and regular execution is in the same way. A team from Stanford and University of Kaiserslautern did this work. And basically what we are working on now in a current research project is that we try to bring such tools and such mechanisms from the software and the hardware world together to be able to build secure systems, because these systems consist strongly depend on software components and hardware components, that we can actually build secure trusted execution environments, because I think these are by themselves a good mechanism to increase the security of systems, be it cloud or IoT systems, because they actually allow you to isolate your computation from the rest of the system. So how can such, in general, how can such attacks be prevented? Either through design verification tools, as we just saw, code reviews. So I think it's good practice to actually open source your designs, because it makes analysis easier. That also helps with the second point. That's, of course, always security testing. Fast testing is very popular, works for certain software bugs very well. The examples I gave here are basically vulnerability research. So we sit down and actually analyze these technologies and to see if there are still any problems left. And that is a slow, expensive, and quite error-prone process, especially since the designs are often not open sourced, especially from the bigger vendors. So it's much more difficult to find these problems. And that is why many of these problems go undiscovered for a longer time. Okay, by that, I would like to conclude. Thank you very much. And I have one little advertisement for CARDIS, which we will host soon.
Thank you, Thomas. When is CARDIS? maybe you can also tell that.
When? So in November, yeah.
November, okay. Yeah.
The publication deadline is still open, so it's it's one more week actually. The submission deadline for papers.
Okay, thank you for the wonderful talk. I mean, would you prefer reading questions yourself, or should I read them one by one?
Sorry, yeah, I see them. I can take a look. So the first question is whether or not ARM Trust Zone is a trusted execution environment. Yeah, good question. I guess that's yeah, it's about definition, right? So it's definitely they are also providing a level of isolation, and yeah, I did not spend too much time working with a trust zone, as it is not as it was the earliest one, and it's not as refined as the others, right? So if they don't see it as a trusted execution environment, I guess they have good reasons for that, right? So the next question was whether it would computer secure more efficient than trusted execution environments. I usually tend to think that in terms of efficiency, trusted execution environments are quite good because you are actually on the, so one alternative is that you have a secure element somewhere in the system, maybe even on the same processor. You could argue that some of the solutions actually use something like that already. Usually such secure elements or hardware security module for that matter that is somehow separated. That brings some advantages, some security advantages in my opinion, because you have stronger isolation with the trusted execution environment. You always hope to do the same thing without leaving the main processor. So more isolation, better protection, but also bigger overheads for communicating, right? So then you need a more precise design. How much encryption, if you want to outsource that, or how much performance do you actually need for your secure element? So I think the approach is quite interesting, as it allows you to do certain things within the refinements of your system without exposing your software to vulnerabilities in the rest of the system. So I think that's actually a nice approach.
Yeah, maybe one more question and then we can wrap up.
Yeah. What else do we have as we? Yes. So SNP is protected even without runtime measurements. Already the main attestation mechanism has been revamped, has been redesigned, and so SNP is protected against this attack. At the same time, also AMD does not, at least we are not aware of any plans that they want to fix this on the older platforms, right? Which is, yeah, so please go ahead and buy new hardware.
Thank you, Thomas. Thank you for the, again, wonderful talk, and thank you for answering the questions. And I think it's time to move on to the next speaker. It's also my pleasure to announce the next speaker, Patrick Chamont. Patrick Chamont is a professor in computer engineering at WPI. He received his PhD degree in electrical engineering from UCLA in 2004, and the MS degree in computer science from Ghent University in 1990. He was a staff researcher at IMEC, Belgium, from 1992 to 2000, and a faculty member with Virginia Tech from 2005 to 2019. And he joined WPI in 2020. He's a Redbud Excellence Initiative visiting faculty with Redbud University in Netherlands. I hope I pronounced it right, from the 2020. And his research interests are in design and design methods of secure, efficient, and real-time embedded computing systems. He served as a program co-chair for several conferences in cryptographic and secure engineering. We all missed these conferences, physical ones, including CHESS, HOST, AS, HES, and FTTC. He received the NSF Career Award in 2007. And he will be, the title of his talk is Hardening Software Against Implementation Attacks Using Parallel Synchronous Programming. And Patrick, the floor is yours.
Thank you, Ozgur. Thank you for the introduction, and thank you also for hosting this talk. So far, the previous two speakers covered attacks. And so my talk will cover countermeasures and defenses. And so I want to address the problem of writing software that is resistant or hardened against implementation attacks, where implementation attacks could be either side channel attacks or fault injection. I acknowledge my sponsor and, of course, my students, as well as my collaborators in this work. So the outline of my talk is has 3 parts. So I'm going to try to sell you to a new programming model, a new way of writing software. I call it parallel synchronous programming. So I will first spend some time motivating why I think that we need a better programming model if you want to deal with implementation attacks. And next, the second part of the talk is going to illustrate how you can build countermeasures against side channel leakage or fault injection using parallel synchronous programming. And I'm shortening it usually to PSP. And then finally, in the last part of my talk, I will cover some engineering aspects related to PSP. I want to start by going back to, what Thomas in his talk was talking about. He mentioned constant time programming. And so in crypto engineering, constant time usually means writing your software such that it doesn't have data dependencies or secret data dependencies. And how do you do that usually? Well, if you read the literature, you will find people say you need to avoid data-dependent control flow and you need to avoid arrays so that you have no cache accesses and so forth. However, what you should realize is that programming languages do not guarantee timing. The execution time of a program is a consequence of it executing on an architecture. And the fact that a program takes longer or whether an instruction creates an exception is an effect of the architecture. It's not something that is in your program. Now, people, especially in the embedded systems community and in the critical applications community, have thought about this problem a long time. Like, how can we write a program that is perfectly predictable in execution time? And one famous researcher in that field is Edward Lee from UC Berkeley. So about 15 years ago, he came up with this idea called precision time machine. And his big idea or his objective was, how can I write a C program that has perfectly guaranteed timing? And by guaranteed timing, it means from the source code, he would be able to predict how long every function takes in execution. And so he came out after a few years to the conclusion that you need custom architecture for this. And so he built this Pret processor. It has many fancy features in it. And I will highlight one specific feature in it, which is easy to explain, which is this processor, which guarantees the execution time of your program. It has an interleaved pipeline enabling 6 hardware threads. So what they realized was that, well, one source of execution time variation for software are pipeline hazards. If instructions in a pipeline as they flow through start influencing one another, then you're basically going to get a pipeline hazard. And so you don't want this hazard. So what you do, well, very easy. Let's say that you insert knobs in between every useful instruction. I'm going to insert 5 knobs so that every instruction is more or less isolated. That works and it avoids every pipeline hazard. But of course, the disadvantage is now your program runs very slow because you have all these knobs inserted. So eventually what they came up with was to interleave several different parallel hardware threads. And that's why you come out with this interleaved pipeline. Now, of course, a Pret machine is not how processors are built today. And how processors are built today, and for example, microcontrollers is just as standard RISC machines. And so the question is, well, could we take this idea of Pret machines and try to build a better guarantee for execution time only using software? And so the answer to that is, we believe yes. And so we call that parallel synchronous programming. It's also a parallel programming model similar to what Pret is supporting, but it gives you a constant execution time in the sense that it could be used to write constant time software. The parallelism that is provided by PSP will be used to build our countermeasures, but that's a point where I come to later. First, I'm going to explain you how parallel synchronous programming works. And it's basically a combination of two ideas. The first idea is bit slicing, which is probably familiar to you who have, some of you who have worked with side channel resistant software development. The second idea is synchronous programming, which I believe is an essential concept to build a complete programming model. Let's start with giving a little bit more detail of each of those, starting with bit slicing. So the origin of bit slicing is also an idea that comes back from almost over 2 decades ago. Was a paper in 97 by Eli Biham that tried to build a high performance implementation of software DES on a 64-bit processor. Now, the problem with DES is that it has these S boxes that are very small. You have a 6-bit input and a 4-bit output. If you map this onto a 64-bit processor, what you see is that most of the bits are unused. That is actually a source of inefficiency. And so what he wanted to do is he wanted to run his DES software faster. And so the idea of bit slicing was actually a performance enhancement technique. And his idea was, well, let's avoid this mismatch. Let's try to write DES using a Boolean function. And essentially a Boolean function is a function that is written in terms of logic operations on a single bit. So it's something that you can think of as a 1-bit execution or a 1-bit processor. And then you have 64 bits in your processor. Well, let's parallelize DES 64 times so that you can run 64 copies of DES at the same time. Now, all of your processor bits will be used all of the time. So it's a performance enhancement technique. Now, how do we write these Boolean functions, right? Because it might not be so straightforward. If you have pure logic operations, and let's say I'm a logic designer and I can already write functions that use only logic primitives, there you go. It's not so difficult to build Boolean functions if you write 1-bit expressions. You use primitives such as nots and ands and ors, and you use expressions that combine these primitives in networks. You can write these Boolean expressions, and once you have them, you have a 1-bit function or a function that is executing with a 1-bit precision. You can map these into bitwise instructions on your processor, and there you have it. You have an automatic version of your bitwise execution on your processor. But of course, that is not enough, because in practice, people want n-bit expressions. For example, you want to do integer addition. You want to do a 64-bit addition, for example. For these more complex operations, what you have to do is you need to break them down into single-bit operations. So the 64-bit addition, for example, would have to be broken out into 64 full adder operations, where if you're familiar with hardware or logic design, you can recognize this as a full adder. Then you have 64 copies of those. That would be your 64-bit adder. But then to run this as software, what you would need to do is to execute each of these logic functions here as a bitwise operation. So you have to schedule the gates sequentially. That gives you your Boolean function in software. So that's fine. Now we can write these, basically anything that you can write as a function with arbitrary complexity in expressions, you can write them as in this bitwise form or in this 64 times parallel form. But of course, we don't know yet how to do control, and we don't know yet how to store bits. That's where the second part comes in, which is the synchronous of PSP. Now, synchronous programming is something that in the software world exists from probably the 80s or so, where people were building safety critical systems programming. And when you build safety critical systems, one of your concerns is to have deterministic execution. Namely, you have to avoid all sorts of race conditions that are so common with software. And so what they invented there is a programming paradigm where state update is synchronous. If you're a hardware designer and you're familiar with RTL, it's exactly that idea. But if you're a software designer, the way you need to think of it is everything that is execution in your program is separated between reading from inputs and writing the outputs. And before you do anything, you wait for a clock tick, which is a global signal in your system that will allow your software to execute starting. Once it's received the clock tick, it reads the inputs, it evaluates the outputs, it reads the inputs and the current state, it computes the next state of the thread. And then at the end, it will advance the state to the next clock tick. This type of model is being used to avoid race conditions. We are going to use this to build control at the 1-bit level. See, the advantage of synchronous programming is that it brings in a way to write control at the level of a single bit operation. And the way we do that is by writing finite state machines. I have here an example, which is a complete algorithm, and that algorithm is that of a greatest common divisor operation. Has 2 states. Initially, it waits for a start pulse. When it receives a start pulse, it will start iterating over 2 state variables that as long as they're different, and it will finish the computation when the 2 state variables are equal. What happens in these states is initially the states are initialized from the input, and then during the execution, you simply subtract the smallest from the greater one until they're equal. This is the standard GCD algorithm. Now, you can map this into Boolean functions, and you need 1 state element, which would be the register here. And that allows you to write everything that you can see here in terms of single bit operations. So now we can not write only just data processing and functions, but we can also write control flow at the 1-bit level. So let's apply this to this GCD. The way this would look like is, well, let's say that you have your module here, whereas this is your synchronous program. It's a GCD that takes in a 4-bit A and a 4-bit B. It waits for a start pulse. Then it will start crunching these 2 numbers, computes the greatest common divisor of A and B, and produces it at the output on Q. And then at the end also produces a done pulse. You transform this into a Boolean function. Then from the Boolean function, you go to bitwise operations. In these bitwise operations, you will essentially make everything 64-fold. You make 64 different copies. In the end, what you get is a function that looks like this, where you essentially have 64 independent threads for your processor. They're synchronous threads. Every time you call this function, every function, and here every bit will compute 1 logical clock cycle of your synchronous program. But so this is the PSP model. It is bit slicing, but remember, bit slicing enough, the functions enough or not enough, you also need a way to have the control flow in there. Now, how do we, this is an illustration of the constant time property. So I mentioned, well, this PSP can execute in constant time. And so this is from a simple experiment where we just take GCD and then a PSP version of GCD, you run it on an ARM Cortex M4. The gray one here is the plain C program. The black dots here are the PSP program. And you see that they're basically now, your GCD is computed 32 blocks at the same time. And the execution will finish when basically the biggest GCD has finished. So the variation of the execution time becomes very small, and moreover is in steps of a single execution of your GCD function. It's not exactly constant time, but that is essentially a consequence that the GCD algorithm itself has a data-dependent loop. If you would remove this data-dependent loop, you would see an exact constant execution time. Now, let's now move to see how we can use parallel synchronous programming to protect against implementation attacks. And I'm interested in something that deals with side channel leakage and fault injection at the same time. Essentially, if you survey the field of countermeasures, you will find that countermeasures very often are based on redundancy. And so you see that in side channel leakage countermeasures, for example, where people take a single bit, split it in 2 bits, that's called secret sharing, it's used in masking. You also see that when people take 1 single bit, split it in 2 complementary bits in order to implement a hiding countermeasure. In fault injection, you do redundancy essentially so that you can sustain a fault and then either correct it or detect it. You use spatial redundancy to protect your data. Let's say that you have multiple bits in a word. One of these bits could be affected by a fault injection, for example, the EM fault injections that Ingrid was describing. If you have a copy of that bit, you can still restore it. You also have temporal redundancy, and temporal redundancy, you need it to protect the instructions as they're executing on your processor. See, your processor might skip an entire instruction. And so that would sort of avoid even data from being changed, but still your program would be faulty. So you have to protect against that as well. That's called temporal redundancy. We use these 3 parameters here, D, RS, and RT, which are the 3 parameters that describe the level of redundancy for each of these aspects. The level of redundancy for side channel leakage, the level of redundancy for space, and the level of redundancy in time. And using that, we're going to apply that into the PSP programming model. And so this colorful slide that you see here illustrates how we allocate bits in, or how we allocate threads in our 32 parallel thread implementation. Of course, the plain execution is when D and RS, that's a spatial redundancy here, are both 1. But let's say that you take 2 redundant copies of every bit, right? Then you see that you have a B0 here, and then you have another B0 there. Similarly, you have a B1 here, and then you have a copy of that B1 there. So you have now 2 levels of redundancy. You can also move to a scheme where you have multiple shares. So you go from D11 to D21, where you take 1 bit here, you split it in 2 masks, and then you take another bit here, you split it again in 2 masks. You see that in total now the number of data bits drops by half, but I have 2 shares per bit. And so using variations of these allocations here, I can implement arbitrary representations for my program. Now, in the coming few slides, I will describe how we now build side channel countermeasures, spatial redundancy, and temporal redundancy using this programming model here. I should say beforehand that most of the programming you can do because it's just as you would do normal PSP programming, namely with bitwise instructions. However, some instructions require interaction between bits, and for that we will need special instructions on our processor. So I'm also going to talk about custom instructions that are being used to build these countermeasures. So let's start with side channel leakage. Now, side channel leakage based countermeasure based on secret sharing or masking is well understood and well known. The difficulty there is really that you need to find a way to deal with the nonlinear functions in your design, and these nonlinear functions are typically multiplications. And so I have an example here that I've taken from a paper or work of Gilles Bart that shows how you do a 2-share secure multiplication here. And so these bold numbers here are actually 2-bit vectors that you have here. So you do an AND operation or you do an XOR operation, that's all fine, but you also have these special operations here which are which affect 2 bits at the same time. So 2 different slices in your processor world. And so these are subvector rotations. To implement these special instructions here, we introduce an instruction called subrotation. And so it basically, depending on your redundancy level, it simply does a partial rotation of bits in your word. But using this subrotation plus the bitwise instructions, of course, you can implement math computations of your cryptographic algorithm. Now, how about faults? Well, faults becomes a little bit more tricky because we need to distinguish between data redundancy as well as time redundancy. This data redundancy means that we are able to detect faults that are being implemented or injected in our data bits. And really detecting or correcting a fault goes through three different phases. At the start of your computation, you need to make your data bits redundant. Then second, you need to do redundant computation. And then at the end, we need to detect faults or correct faults. We implement a redundancy here as a complementary redundancy. So if we have a data bit that is 1, then the complementary version or the redundant copy of that data bit will be a 1. And the reason why we do that, why we make them complementary, is that fault injection, or we believe that fault injection tends to affect bits in a processor world in the same way. If you have a stuck at 0, then the chance to find a stuck at 0 somewhere else in that processor world is quite high. So if you make them complementary, you have a higher chance of detecting faults. Now, once you do that, of course, you have these complementary bits. Your computations also need to become redundant. If you are doing logical AND right here, then you will have to do a logical OR at the other side. Remember the Morgan's law. So for this reason, because these instructions here, they still work on one single processor world, we need to implement these special custom instructions here that help us to do redundant computation. But all in all, so to implement complementary or direct redundancy in our processor, we have these 3 types of instructions that we have introduced. One, to convert or inject redundancy in a processor world. One, to do redundant computations. And in the end, one instruction to check faults or correct faults. And so many of these instructions have immediate parameters, which means they implement several different variants internally, depending on what type of protection you want. Now, how about temporal redundancy? You might wonder, well, why would you need temporal redundancy using PSP or using any software mechanism? It's simple. You simply execute your function 2 times. That's temporal redundancy. I want to point out that because of the parallelism inside of PSP, we can play a trick that is actually saving us a lot of overhead, or that makes our latency of our algorithm much smaller. Many cryptographic algorithms are iterative. They work as rounds, right? This is the original copy. Now, when you build a temporal redundant version of it, it would mean you implement several different copies of that round inside of a processor world and several different bits. Now, we can offset the execution of these rounds by 1 round. For example, the left bit, we start round 0 first, then we move to round 1 and so forth, and all the way at the end you do a knob. Whereas for bit 1 here, you first do a knob, then you start computing round I-1 and then round and so forth. You see that right here during the execution, you have several different rounds executing at the same time. And the reason that works is that, well, because round I and I-1 in terms of instructions do the same operations, it's just that they work on different data. And so this way, if you take out an instruction here, somewhere in the middle, we can easily detect it at the end. So that's one way you can implement temporal redundancy. So you see that the 3 techniques that I've discussed, data side channel resistant by secret sharing, or spatial redundancy, or temporal redundancy, they can all be supported by PSP. And we actually build a processor that does this, that build all these custom instructions that helps us to execute AES. And this is just one measurement I'm illustrating here, where we built a scheme of 4-1. So you have 4 shares and 1 spatial redundant bit. So this is a 3rd order side channel resistant implementation of AES. If we keep the random number generator off, which means you don't have randomization, your masking doesn't work, you see that your side channel leakage fails. It fails the TVLA test here. Whereas if you turn your random number generator on, even if you have a lot of traces, you stay within the constraints of your TVLA test. So that gave us confidence that, yeah, you know, with this PSP, we can build countermeasures with it. And moreover, they're comprehensive. They deal with faults as well as with power-based side channel leakage, as well as with time. Remember, they also have this constant time property. But of course, we still need to write these PSP programs. So how do we write one-bit programs? Who wants to write a netlist as a software program? We need some design automation to make it more easy. And so we have a design flow there where we start. So this is our vision of the design flow. We don't have everything of it yet, but you start with C code. You can first, you need that FSMD model, because that is your synchronous programming model that you're going to parallelize into PSP. So you can do that using high-level synthesis. Once you have your synchronous version of your algorithm, you use logic synthesis to build a gate-level version of your algorithm, right? At which level everything becomes individual gates. And then finally, once everything is at the level of just single Boolean functions, you do bitwise expansion. So you replace all of these operations by bitwise instructions, and now you have your PSP program. We have a version for this that helps us to make this step for the case when we have described this using Verilog, so using a hardware description language. The reason why that works is that RTL semantics in Verilog are the same semantics as synchronous programming, as the same semantics that we need. So we are using an open source logic synthesis environment called Muses. We have a C code generation backend for it. We can retarget it to different CPUs, RISC-V or an ARM. And we can also automatically inject these countermeasures, basically that are exploiting the redundancy between the different slices. So we can automatically inject those. So that helps us do many different examples, because now we can take any open source hardware that we find for a crypto algorithm and then build a PSP software version of it. It's kind of funny to notice that many people have tried to convert C into hardware. And here what we're doing is the opposite. We take hardware and we convert it into C. So now let me, the last part of my talk, let me say a few words about hardware acceleration in PSP. I have already mentioned these custom instructions that we need to implement our countermeasures, but these custom instructions, they really have a functional requirement. They need to be there because the countermeasure requires it. At the end of the day, I also want fast programs. So what can I do to make PSP programs run faster? And one particular operation that I'm going to focus on is the transposition operation that is needed for any sort of bit sliced execution. If you have, let's say, remember this GCD program at the beginning, if you would have 64 different GCD inputs, then what the algorithm actually wants is one variable that contains all the 0 bits of all the values here, the second input that contains all the 1 bits, and so on. And so this is called the transposition operation. You need to do this before you can feed algorithm into a PSP program. At the end, once you have completed your computation, you need to do the opposite. You need to take your transposed outputs and make them back readable towards normal people. So that's your standard output data. Usually this is done in software, but this takes a lot of time. I'm going to show you how much time it takes. You could wonder, well, can we do this faster? Can we do custom instructions? Can we maybe do even a dedicated hardware module? So that's what we try to figure out. We have one instruction here, we call it TR2, and then the inf TR2, depending on what direction you go, that takes one step towards this transposition. And so it takes this particular transformation here. You take 2 registers, you apply TR2 to it, and you see that it reshuffles the bits in this pattern. If you now apply this TR2 in an FFT-like fashion, if you're familiar with fast Fourier transform, it's a similar flow. So you apply your TR2 like this. What you will find is that in this case, this is for a byte level transposition. It transposes exactly all of the bytes in your flow diagram. So this is nice, but you see that it still requires quite a lot of instructions. It's a lot less than what if you would do this straight using software instructions alone, but it's still a lot. So can we do better? And so, well, if you take a step back and think where your data is stored, typically before you start processing, is in memory. So why don't we try to transform the data as it moves from memory into the processor? So we have this module here, we call it a TDMA, it's a transpose DMA, that helps us to copy a block of data from RAM into the processor. And while it's flowing into the, well, it actually goes, it copies from RAM into another location from RAM so that the processor can directly read it from that location. But as it reads it, it is already transposed. And so the DMA module does more than only the transposition. It also deals with the redundancy features that we need to have. So for fault redundancy, we need to copy bits or complement them. For side channel resistance, we need to mask bits. We need to inject these, we take one bit and split them in shares. All of this is taken care of by this DMA, which saves a lot of time in execution. And to just illustrate how much execution time, this shows you the cycle count on a RISC-32 processor, where we transpose a block of 32 by 32 bits or by k bits and then 32 words. And so the quadratic function here, that is the cycle cost for pure software. Mind you, this is like 50,000 cycles at this. Whereas the two lower numbers here is when you start using custom instructions, we have the Skiva version 4 RISC-V, or when you use the DMA module. And even if you compare the DMA module, it's still a lot faster, 3 times faster than using custom instructions. So yeah, you can also optimize performance from these PSP programs. So finally, let me give you a few pointers towards our artifacts as well as publications. First, is these are a few artifacts that are available on GitHub. We have an open source version of Skiva. The version here is for Leon 3, where it runs on an FPGA board, so you can download it and then try to do side channel attacks on it. We also have several benchmarks using the PSP model. So we have one that we did for the NIST Lightweight Crypto meeting last year, where we have several different of the candidates. We also built one where we just looked at several different algorithms and then built PSP versions for those. Finally, I would like to acknowledge the work that I'm presenting is work by many people. So these are all the quotes from the papers here have contributed to this work. All of this, you can find it online if you want to know more details. So let me finally make some conclusions. So the point I'm trying to make here is that building countermeasures is important, and building countermeasures requires design automation. In order to build your design automation, you need to, it is useful to sort of go back to the basics and to wonder like, well, why are things breaking today? For example, the constant time programming that you try to do in software, it's fine to think of better ways to write your C code, but you have to realize that writing C code is not the root cause. By going back to the root cause, you can come up with different approaches or fundamentally different approaches to deal with those defects that you're trying to resolve. And so that concludes my talk. And I'll be happy to have to answer some questions if you have questions.
But this is Erkay speaking here, so can you hear me?
Yes.
All right, thank you very much. That was a really, really interesting talk, and there are like questions, but I maybe we can go through them. But you know, you already answered some of them. I mean, if you can go ahead and read the Q&A box yourself. But those are kind of early questions, but you just somehow answered some of them already. But if you want to,
let me go. Yeah, there's one that says batch operations, right? Batch operations are, so batch operations, so that's a very good point. I would say though that in PSP, so this is exactly the point where you can get out of the batching concept. In classic bit slicing, indeed, you have this batching. Sorry, everything needs to run at the same time. However, when you run in PSP, you can start and stop every bit separately. So you can run this completely pipelined version of where every different bit slice or every different slice runs a different round of your cryptographic algorithm. So I think we have not studied this in detail, but I believe that there are ways to deal with this latency effect that you get. Then there's also, it's painfully to write by hand and almost impossible to review by third parties. That is true. Are there tools to automate the generation of native to bit-sized representation? So I covered this, right? So yes, we have a coded generator. We haven't open sourced the coded generator yet. That is something that we plan to do, but it's just that it's not, we are not there yet. You can find on the pointers that I give you contain several different benchmarks. So you can find versions of C code that has been bit sliced using our coded generator. Then there's a question of Costas. Could you repeat why we need such transposition in a bit-sized representation? Well, simply because if you want to work with, let's say, 5-bit quantities, right, you think of a 5-bit word, but you know that your programming model, your processor can process only 1 bit at a time. So you have to feed it in bit by bit. The fact that we transpose this is because we want to create this parallel version of our algorithm where we do bit by bit for many different copies of the algorithm at the same time. That's why we have this transposition. And then there is a question on domain-specific applications like deep learning and model. That is a very good question. And is there memory restrictions? So regarding let's take deep learning models. I would say yes. And especially where it is advantageous is where you start running into applications where the word length of your application does not match the processor. And you have seen this definitely in deep learning applications. We have all these neural networks where they start doing 3-bit multiplications and 2-bit multiplications, which would be very inefficient when you want to do them using standard processors. And that's where all these neural network accelerators are going for. They build these reduced word lengths. However, if you get the point of PSP, you can actually also do this in software. And in fact, we wrote a paper, I referenced it in the talk, where we show that you can actually outperform for a neural network, for a matrix multiplication of reduced word length. You can outperform hardware multipliers simply by reducing the word length enough. And at some point, it simply is the processor word length becomes inefficient. So I would say, yes, it's definitely worth to look into PSP applied to different domains, and you would use it at any domain where you need exotic word lengths. And I think I've answered all the questions.
Thank you very much, Patrick. Fantastic. You answered all the questions. Yes, thank you very much. Let's see once more. Yeah, you did, in fact. Thank you very much. It's a fantastic, the talk. Thank you very much. So with Patrick, we just finished the first part of our webinar. We are, running a little bit late, and we are supposed to start at 5:45 p.m. If it is okay with Christoph and Francisco, maybe we can just, take a break until 5:50 Turkish time, until 50, if it is okay. So let's take a 6 minutes break. And we are going to come back at 6 minutes later. Thank you very much. Hi, we are back and we are ready to start the second half of our webinar. So we have very exciting talks here. So we are going to start with Christoph Paar. Christoph Paar is here, and Christoph, I'm going to read your bio while I'm reading it. So you can just basically start sharing your slides if you like, and thank you very much for joining us. All right, so I'm just Professor Christoph Paar is together with Gilles Barth, founding director of Max Planck Institute for Security and Privacy in Bochum, Germany, and a research professor at the University of Massachusetts Amherst. He co-founded with Çetin Kayakoç the Chess Conference. Christoph received an ERC advanced grant for research in hardware and security, and is co-spokesperson of the DFG Cluster of Excellence Cybersecurity in the Age of Large-Scale Adversaries. His research interests include hardware security, applied cryptography, and physical layer security. He is fellow of the IEEE and the IACR, International Association for Cryptological Research, and has given invited talks at Harvard, MIT, Oxford, Stanford, and Yale. And his talk title is going to be Hardware Security in the Age of Large-Scale Adversaries. Christoph, thank you very much for accepting our invitation and joining. Thank you very much, and you can start if you like. Thank you.
I'm real. It's not. Okay. Yeah. So yeah, I want to talk, give overview about the work we've been doing with respect to really what's hardware Trojans. So this is mainly work we did a few years ago. I'm also do more current work in that area, but I thought maybe for this kind of forward-looking workshop here, it might be best if I give an overview about the fundamental work that we did. First of all, there are 4 parts to my talk, 2 kind of introductory parts, an introduction to hardware Trojans, and then a historical viewpoint. And then I want to talk about 2 technical topics where we actually built low-level hardware Trojans with 2 case studies. Okay, so what are hardware Trojans? It's pretty self-explaining, the term. An adversary adds some unwanted functionality to a digital circuit. So why would people do that? Oops, wrong direction. Why would people do that? Well, there are many unpleasant applications for that. A big motivation actually in this whole research area that started about, I would say, close to 15 years ago, started by the Department of Defense in the US. So they are worried that the chips that they're using, because they're manufactured overseas in East Asia typically, that they don't have the original functionality. Standard example is you're flying a drone and the drone works beautifully unless it's over a certain country. Let's say unless it's over China, or unless it's over Germany or Turkey or whatever, right? Because, for instance, the German Secret Service implanted a hardware Trojan that we've seen the ransomware attack, right, a few weeks ago on a critical infrastructure in the US. A similar attack is, of course, also would potentially be possible with hardware Trojans, right? Because everything, as we've seen with this ransomware attack, that the infrastructure has become digital. But also we could probably look at personal electronic, and here we could, for instance, imagine a whole bunch of privacy violation because, for instance, the main CPUs is equipped with certain hardware Trojans, right? Which would, again, be a very unpleasant outlook. I'm going to talk a little bit in one slide about the scientific community. You see here, this is this DoD report from 2005, so about 15 years ago, entitled High Performance Microchip Supply. It should really have, a more fitting name would have been High Performance Microchip Supply Crisis, right? So that triggered a lot of research, and many people in the room have been doing work in crypto hardware and hardware security for a couple of decades, just like me. But until this report came out around 2007, there was hardly any work being done. What you see here is statistics on papers that have been published that deal with hardware Trojans, either in the title, that's the lower line, or dealing with hardware Trojans somewhere in the paper. So that's this paper statistic we did a few years ago. So what I'm trying to do is this report by the American DoD triggered a lot of work in our scientific community. So, one valid question is, how does it really work in detail? How would people inject Trojans? the original concern in this report I just mentioned was during manufacturing, actually in the fabs, that people inject Trojans, which is pretty difficult. A somewhat easier approach would be that you build Trojans in IP cores. It's hard to get, it's difficult to get hard numbers, but it said that in the iPhone main chip has up to 200 IP cores. So, you know, we could imagine that there's some of these, that also means many of the IP cores are not fully trustworthy. So, you know, and it's not too far-fetched to imagine that, you know, let's say a hostile nation state succeeds with implanting malicious IP cores, right? Something like a UART driver or something like that. But there are other ways too to do that. For instance, during shipment, right, by swapping integrated circuits, or built in by manufacturer, which we would probably call backdoors rather than hardware Trojans, but in terms of functionality, that's the same. It's kind of interesting to look at who is interested in that. As I mentioned before, these attacks, this is something governments, not only the US government, I know also other European governments are very worried about that, you know, maliciously implanted Trojan. At the same time, we know from the Snowden revelation that governments, essentially the same people, also like to inject Trojans, for instance, in this way. If you go to the Wikipedia, the English Wikipedia, and you look at NSA, you'll find this photo. So this is taken right from Wikipedia, secretly, a secret photo taken within an NSA facility, and allegedly people are opening up boxes and adding malicious chips to that. So there's a certain duality here, right? Yin-yang thing, right? That means governments probably all over the world like implanting Trojans at the same time. They're very worried about Trojans being injected in their own hardware. So I think it's an interesting situation. Okay. It's very hard to find real-world case studies on that, but historically, in the last 60 or 70 years, there have been quite a few interesting occurrences, okay? Some of you might know Boris Hagelin. He was Swedish. He built this M209 encryption machine, which was used by the US military forces during World War II, kind of the counterpart to the German Enigma, with the noticeable difference that it wasn't broken. It didn't get broken, okay? After the Cold War, Boris Hagelin set up shop in Switzerland and started a company called Crypto AG, right? And again, this is the person who, during the World War II, supplied cipher machines to the US military. This is a picture of Crypto AG in Switzerland, the company. And what came out, actually repeatedly, is that Crypto AG cooperates with, you know, some of our favorite national security agencies, meaning the US, British, and the German Bundesnachrichtendienst here, right? And how they're collaborating actually by artificially weakening these cipher machines, right? So there's a strong indication that the standard machine that they used was artificially weakened, meaning that those nations could read traffic that was encrypted with this thing. There's a very prominent case was actually in my youth, while I was an undergraduate student. There was a bombing in Berlin of a discotheque, which was frequented by US soldiers. I believe a few people also died there. And a few days later, Ronald Reagan performed airstrikes against Libya. And the reason for that was, and Reagan misspoke, it became clear that the Americans were able to read the encrypted traffic between Libya and the Libyan consulate in Berlin. So that was a strong indication that the encryption was not secure, that was being used. Yeah. Then what happened during the 1990s, the so-called crypto war started, and many in this room remember that, right? In our lifetime, until the late 1990s, you were not allowed to export product with cryptography with keys beyond 40 bits, which of course even back then in the 1990s was very insecure. And there was a big international discussion about that. And in 96, there were major relaxation in the United States with respect to crypto export, right, which was actually done by Bill Clinton, but there were actually the Europeans that put a lot of pressure on the US to do that. Much more recently, you know, I think that's the second to last slide on that, right? That's the former FBI director here. You know, he's really worried. He said, okay, you know, we're going dark because there's this strong cryptography through end-to-end encryption, right? For instance, WhatsApp is using that, right? And then it was again proposed that we should use crypto backdoors so that, you know, it would be easier to find criminals and terrorists and so forth, right? An example that governments actually are putting in backdoors is this dual ECC random number generator, which there were indications to that again in the Snowden files. So that was an example where actually governments implemented or injected Trojans or backdoors, not in a product per se, but in a standard, which is a very sneaky way of doing that, right? So where are we now? This big discussion, very current, is about foreign-made equipment. There was this big uproar in the Bloomberg article, and there was a question whether backdoors built in routers and servers, right? And up till now, the jury is still out whether that was valid or not. What's a very big discussion all over the world is can we trust mobile communication equipment, right? There's if I'm not mistaken, for instance, Britain doesn't allow the usage of 5G equipment coming from Huawei. So what you see, this whole topic of hardware Trojan also has a big important political component, and it's quite important for us as a society. Okay, so this was kind of the big picture thing. Now I want to talk a little bit about case studies that we've done over the last few years. So these were the people that drove that here, you know, Georg, Pavel, and Mark. So despite the examples I showed, which is kind of interesting, there are very few hardware Trojans observed in the wild in terms, that means hardware Trojans that we would perceive as hardware Trojans, right? There are a whole bunch of examples, but they're typically done by people like us, right? You know, my master students, they build some hardware Trojans in FPGA, right? The big question is this relevant on how similar are there to hardware Trojans that governments would actually build, right? And you remember this publication numbers I showed you before. The vast majority of publication actually focus on detection rather than on designing Trojans, which gave rise to some considerations that Georg Becker and I had a few years ago. And I mean, we thought, why don't we design Trojans, and just designing in introducing Trojans their own design is usually trivial. And, you know, we're researchers, we like it hard. So we had this additional requirements. So we try to design Trojans that are particularly hard to detect. So the question is, what is the minimal change that we can make to a hardware circuit and still end up with Trojans that are useful for an attacker? Okay. So we start with an inverter Trojan, right? And if you look at a modern integrated circuit, right, as we all know, they consist of millions or even billions of transistors. So we look at the most simple circuit that we can have, namely an inverter, right? We all seen that, right? The CMOS inverter. And what we're going to see in a minute, we try to manipulate that transistor in a sneaky way. The functionality we would like to have is this. So rather than having an inverter with a real function, right, that inverts the input signal A, we want to have a static output of Y. So now, and later on, we will see that this, if we can do that, we can actually build very dangerous Trojans from that. So an easy way of doing that would actually be a change in the metal layer of the integrated circuit, and have essentially what you see on that slide here. The problem with that, this is pretty easy to detect if you actually change the metal layer. So the question is, are there more subtle way of doing that? And Yes, there is. So let's look at this transistor. So this is this PMOS transistor that we are observing, right? And of course, this is not to scale, right? If Intel is talking about 7 nanometer technology, this is typically the gates width here, right? Or the gate length, I think they call it the gate length, right? So this is, in reality, this is pretty tiny, right? This is not as big as your screen. So what you can do, rather than injecting p-dopant, you can inject n-dopant. The transistor that you get is now not a switch anymore, but it's always 1. And this is what we did here, right? So the topmost transistor was manipulated in this way. And you can do a similar manipulation with the NMOS transistor in the bottom of your inverter, and so that you get an open switch. If you have that, you have this functionality, right? You have a constant 1 output. So the questions that we have to answer, one is, can that be detected? And secondly, which turns out to be actually the bigger question, how to build useful Trojans from here. And of course, usefulness is defined with respect to the attacker, the adversary. So the question number 1 is actually fairly easy to answer. So this is kind of a hypothetical slide that I hit. So this is how both transistors would look. They would look identical, right? And why is that? The manipulation that we propose here, this is literally on the atomic level. So we're changing just a few atoms in a few selected transistors, and they're very, very hard to detect. I'm going to talk in a few slides. I'm going to talk a little bit about how difficult that might be in practice, right? But it's very hard. So now I'm going to talk about the second question. So what we can do now is essentially we can do a stack at 1 fault, right? So this is a pretty simple era of fault that we have, right? So the question is, how can we exploit that? And so what we're doing, the concept is pretty simple. We're not targeting this multi-billion transistor chip on a functional level per se, but we're only looking at a true random number generators. And probably most people in this room know modern CPUs, yes, they are equipped with TRNGs. They have random number generators out that you need for things such as secure web browsing, email encryption, signing of documents, and. Interestingly, these are all acts, these are all actions we take as a user, which are interesting for an attacker, right? Because they have to do with security. And now the idea is to inject a dopant Trojan here at this point. And there's a disclaimer. This attack, we targeted Intel because Intel had published their TRNG design, but the basic idea works against all modern TRNG, which has to do with the following observation. So modern random number generators work as follows. They have really 2 modules. They have this entropy source, which is some kind of analog circuit, right? For instance, 2-ring oscillator. So the entropy source, they work pretty nicely, but not perfect. For instance, if it's really hot, there might be a bias in the bits that are designed. For that reason, in practice, there is a digital post-processing taking place. And only after the post-processing, we get our cryptographic keys out, for instance, right, out of our random number generator. So, in this setting, there are 2 to the 128 cryptographic keys. That means there's no way we can ever brute force it, right? So the idea now, again, is to inject the Trojan in this here. And what we did at this point is the digital post-processing uses AES. And what we did, we fixed the input to AES. So instead of 128-bit random input coming from the entropy source, we reduced that to 32 bits. That means 96 bits are always assigned a fixed value due to the Trojan insertion. And the remaining entropy that we get out here is 2 to the 32. Meaning, maybe if I stay here, instead of 2 to the 128 cryptographic key, which is again an astronomically large number, we only have 2 to the 32, which is a very nice number. And so this is kind of in a nutshell what we're doing here. And if you look at the actual number, so if you want to brute, oh yeah. So the AS that they're using, they're feeding this entropy source not only to the 128 input bits to AS, but also to the key. So the total entropy with which we feed our AS implementation is 2 to the 256 bits, right? So if you want to brute force that would be the lifetime of the universe. But what we did here, because we fixed almost all input bits to the AS implementation by using this hardware Trojan trick, right? By manipulating the transistors. So we can brute force to this 2 to the 32 in a few seconds with our laptop. But interestingly, from a user point of view, we still get 2 to the 32 different cryptographic keys. So this is about 1 billion different keys. That means for a user, it's at least at first glance, it's not clear at all that there's a manipulated TNG running in the background, right? So the big conclusion from here is, first of all, we published it as chess 2013, I believe. And at chess, it wasn't even such a big thing, but then I think it got picked up by Schneier and Slashdot, and there was a whole bunch of publication following from that. I think the big message we can take home from here is that we showed that we could build pretty dangerous hardware Trojans without adding a single extra Boolean gate, right? We just disabled a few flip-flops really here, right? Most of the detection techniques that have been proposed don't work against our Trojan. Again, this is a reference. What I would like to mention, which I found extremely positive, is at the next year's chess, people from Japan, including people from Mitsubishi Research, showed that this transistor manipulation is actually detectable using an electron microscope. It turns out it's pretty slow. So if you want to scan an entire chip, that might take days or weeks. But nevertheless, so there are countermeasures available. So I was very happy seeing that. So now I want to talk about a second case study with respect to Trojan insertion, which has to do with FPGAs. And we're focusing on what are FPGAs? These are reprogrammable hardware devices. They have many applications. The world market, I think these are numbers that are a few years old. There were about 5 billion devices sold worldwide, right? So this is a tiny fraction of the worldwide IC market, but the absolute numbers, 5 billion, is pretty high. What you see, they're used in many kind of safety or security critical applications, such as aerospace or network routers. So what the idea that Pavel and I had a few years ago, wouldn't it be a good idea to introduce a Trojan in an FPGA? The advantage of that is we don't have to collaborate with Intel, right? Intel would never collaborate with us, right? These FPGA Trojans, these are homegrown Trojans. They make beautiful PhD CVs, right? So in order to do that, I have to explain a little bit how modern FPGAs work. Namely, they have a configuration file, a software, if you wish, that configures the hardware, right? For technological reasons, this configuration file is always stored off chip, and the FPGA is only configured during power up here, right? So this is how it works. That means if you, for instance, have a crypto core, an AES, that you need for your network router, you have to program that into your bit stream, right? This is trivial, right? And again, Pavel and I were wondering, how can we manipulate that? And the basic idea that we have is simple, namely, this time we're not going after the TNAG, but we go after the crypto algorithm itself. That means we're using AES, which is the most widely used block cipher, symmetric cipher, and to replace AES to this version T on the right-hand side with the red T, and T stands for Trojan, right? So the idea is, rather than using the original bit stream, we flip a few bits and have a faulty AES built in. And now I would like to discuss, first of all, how do we do this bit flipping and how do we exploit that, right? And that was actually quite a bit of work. How do you find AES in an unknown bit stream? And we were lucky because the S boxes are very specific. They're very specific entries for the S boxes. What you see here, we found 8 implementation of AES on the internet, so they're not our own. What's really important is just the column on the right-hand side. So with our detection algorithms, we were able to find all the S boxes, no matter how they were implemented. And again, if people know symmetric cryptography, you know that the S boxes have to fulfill certain mathematical properties, in particular high nonlinearity, and you can search the bit stream for that mathematical property. Okay, so now I want to show how to exploit that. So again, what is the setting? So the attack scenario is that the attacker has temporarily access to a device that he wants to exploit. So what he or she can do, you can inject weak S boxes in the bit stream, right? And then you power the device up, and what you get is you get a Trojanized version of AES. So what you can do now, you can feed plain text into your device. You get ciphertext out, but be careful, you get ciphertext of this wrong, of this incorrect AES. This is a Trojanized AES here. And what we saw, and other people said, well, this is kind of cute what you're doing, but what you do, your AES implementation is not compatible with real AES. So the question is, how does this lead to security weaknesses? And we found actually two exploits. First one is related to cloud computing. In cloud computing, there are two things happening. First of all, it's very desirable to encrypt data before storage. So that means if people hack into a cloud server, you only find encrypted one. The other thing, which is very specific to cloud storage, if you do that in hardware, for instance, an AES accelerator, you would use the same AES implementation for encrypting and decrypting. That means at this moment, it would be perfectly fine from an attacker point of view to use this weakened version of AES, because you would write and encrypt and store data with this weak AES. And when you read it out, it would be decrypted with this incorrect AES. That means the user wouldn't notice, but an attacker just has to hack into the server, would get access to the ciphertext, and because the ciphertext is based on a weakened version of AES, it can be broken. The other attack is a key extraction, similar to what you actually see on the slide up there. So let's say your goal is to extract the AES key. What you can do, you simply feed in plain text, you get your ciphertext out with this weakened AES, and because it's a weak version of AES, you can compute the key. So that would give you an easy way of extracting an AES key, and you don't have to do fault injection or side channel attacks. So again, with this, at least conceptually simple manipulation, you could still build dangerous attacks here, we think. So what is the conclusion from here? Well, we think that's a new attack vector against FPGAs that hadn't been exploited before. As I mentioned before, in terms of methodology, this is great because your graduate student can design their own hardware Trojans. You have to the countermeasures bitstream protection, but this has proven to be very difficult. There's a whole history of people attacking bitstreams, including work by Mike in my group at Usenix, where he broke a whole bunch of Xilinx devices. Okay, and the details are in an IEEE CAT paper for that. Okay. If you want to learn more about cryptography, people know that you find my YouTube channel, right? With the Introduction to Cryptography, free of charge, feel free. Okay, that's the end of my presentation. Thank you very much.
Thank you very much, Christoph. That's really exciting talk, really scary. It's really, you can do many things with those hardware, Trojans, and it seems that you can do anything, at all. So that's scary. Okay. So, Christoph, we have some questions in the, the Q&A box. Previously the participants couldn't see the, the questions in the Q&A box, but now they can. Yeah, so, please pick anyone you want and then just.
Okay. So I start with the first one. Yeah, so that's an excellent question. So the first question is, how do we distinguish between hardware bugs or features, right? There's not a strict distinction, but I would say there's something I have not talked about. People, and these are probably very often nation state actors that have interest in building hardware Trojans. they typically want to build Trojans that can only be exploited by them, right? That means there is, and if you read the details of this random number generator Trojan that we proposed, there's some inside knowledge, namely which of the bits you fix to 0 or 1, which is only known by the Trojan designer. And that, I would say, this is could be used as a distinguisher between, bugs which are available to everybody who knows about them, or Trojans that are so designed they can only be exploited by the designer because there is some inside knowledge necessary. But it's an excellent point you're raising. So the next question by Anes, isn't it possible to design algorithms that at least can detect Trojans probabilistically considering TNG? Yeah, so this is a big question, how to detect that. And of course, there is testing involved. And if you look at at our paper, we actually go through great lengths to avoid detecting by testing. But in principle, there are testing approaches that at least makes it much harder to have the Trojan undetected. Just to give you a keyword, people that have a background in cryptography, when I talked about 2 to the 32 keys, it seems a lot, right? They might be hard to find a repeating key. But in reality, you have the birthday paradox. So in reality, with these parameters that I showed, you would actually have a collision after 2 to the 16. So there are certain ways of testing 2 random number generators where it might be not quite as easy to build a Trojan that goes undetected as I did here. But so yeah, you can work on testing. Yeah. So there's Zashin related to the Trojan. I expect that online monitor of TNG bitstream will catch the Trojan. Actually, the online monitor, well, first of all, the online, no. In that way, what you describe, the standard, these health checks, this runtime checks of TNG would probably not catch our manipulation here. And that has to do because there's still there is a sizable entropy pool there, right? So the question is, are there tests that can distinguish between, let's say, 2 to the 128 bits or 2 to the 40 bits mainly, right? And modern, at least the standardized lifeline test, the health test, will not be able to distinguish that, yeah. Okay. So the last question, no, I don't know the last question, a whole bunch of questions come. Which direction are interesting for future and hardware Trojan with respect to cloud security? I'm a little bit unsure. I think also from a research point of view, to be honest, I mentioned that in the beginning, the problem with hardware Trojans is if you're really the designer of the hardware, it's pretty easy to design meaningful hardware Trojan that goes undetected. So, what we typically in our research we're looking at as a general guidelines, how can we build Trojans that are very hard to detect? Which, and if you follow the Huawei discussion, if you talk with your local governments, this is what people are really interested in, right? This is what worries them. So this as a hand-waving general line of research, how can we build stealthy, hidden hardware Trojans? Yeah. Okay, so there's a lecture. Okay, so there's a question whether I'm going to release more YouTube videos. I always wanted to, but I don't know whether people know I left University of Bochum. I switched to Max Planck Institute where I do less teaching. Right now, it's not on my to-do list. I should probably. Next year I might release one more video on post-quantum cryptography. Okay. Okay, so I think I'm coming to an end, and I'm sorry, Erka, I think I went over time. I mean, everybody who knows me knows that I like to talk. So, but it's you shouldn't have invited me. So.
No, it's okay. No. We are really, really happy and honored to have you here, Christoph. Thank you very much taking up your time and coming all the way and then just answering all the questions. And by the way, your videos are very popular among my, students as well. I mean, they are just thanking you.
That's very nice. Thank you. Yeah.
So when
very polite students. Very polite students. They're more polite than German students.
All right. Thank you very much, Christoph. I mean, it's really great, and you're fantastic. Thank you very much.
Thank you.
So, yeah. So what we can do right now, we can switch to the next speaker. Next speaker is a very good friend of mine, Francisco Rodriguez Enriquez. I hope he's still there. Francisco. All right. Okay, Francisco. Right. Let me read your bio first, and then you can basically try, sharing the screen. I mean, while I'm reading the bio. And Francisco Rodriguez Enriquez received his PhD in electrical and computer engineering from Oregon State University in June 2000. From July 2000 to May 2002, Dr. Rodriguez Enriquez was collaborating as a security architect for IT companies in Germany and the US. Currently, he is a professor in the Computer Science Department of the Advanced Research Center Sinvestav IPN at Mexico City, which he joined in May 2002. Dr. Rodriguez Enriquez has co-authored over 80 technical papers and several book chapters. He is also the first author of book Cryptographic Algorithms on Reconfigurable Hardware, published by Springer in November 2006. Dr. Rodriguez Enriquez is co-founder of the International Conference on Cryptology and Information Security in Latin America, LatinCrypt, an advanced school on cryptology and information security in Latin America, which are considered the leading cryptographic periodical meetings in Latin America region. Dr. Rodriguez Enriquez's research interests lie in cryptography, computer arithmetic, and information security. And he's going to talk about post-quantum or quantum cryptography, and the title is that How Long Can We Safely Use Pre-Quantum ECC Elliptic Curve Cryptography? And thank you very much for accepting our invitation and taking up your time to give this nice and interesting presentation. Francisco, floor is yours.
Thank you very much for the invitation, Erkay, and I hope you can hear me well.
Great.
Okay. Yes, thank you very much for the invitation. As Ingrid mentioned, it's a pity that we cannot be physically in Sabancı University and visit beautiful Istanbul and friends overall, but we are here and happy to talk to you, to all the audience, about what could happen with ECC. So the title of this talk is How Long Can We Safely Use Pre-Quantum ECC? Knowing that we have this threat that quantum computers are coming. So let's start. So elliptic curve cryptography. Let me give you a brief timeline of ECC. I try to cover most important things that happened during the creation or the discovery of elliptic curve cryptography, even starting from the very beginning, which is the Diffie-Hellman protocol that was, as everybody knows, was published in 1976. 1 year after, RSA came out in 1977. And then 1 year after RSA, the McLeese crypto system was published by Professor McLeese. McLeese is now one of the candidates for the post-quantum contest that the NIST organized starting in 2017, as we will be talking later. So this was before elliptic curve cryptography. Elliptic curve cryptography was proposed independently by Professor Neil Koblitz and Professor Victor Miller in 1985. And then the reception was maybe not as warm as one could have expected. Some time passed until ECC really took off as the main crypto system that we are using right now. For instance, in the mid-90s, several attacks against ECC were published. For instance, one famous attack is the MOV attack, which was published in 1993. This attack showed that if you were using some specific kind of elliptic curves using bilinear pairings, you could solve the discrete log problem, which is the hard problem that is behind elliptic curves. So care should be taken in the way that you choose elliptic curves. Fortunately, that was a very small family of curves, so that didn't prevent elliptic curves to flourish. 1 year after, one algorithm was published, Shor's algorithm. This was a very peculiar algorithm, but because it was supposed to, the only way that you can execute this algorithm is if you have a large scale quantum computer. And so at that time was mostly a theoretical algorithm showing that if you have a quantum computer, you could break RSA and also elliptic curves, discrete log problems, which is the hard problem that is behind elliptic curves. So that was in 1994, and we will be talking a lot about the Shor's algorithm later. Then in 1998, Professor Frey published the Bell descent attack. Actually, he was talking about that in one of the ECC workshops. And then this attack was later improved by, for instance, right now is known as the GHS descent attack by Galbraith, Hess, and Smart. And this attack is against some kind of family of elliptic curves, binary elliptic curves. And since then, binary elliptic curves were not used that much anymore because there was some concerns about the security because of this attack. But it is important to mention that this attack can be applied only to some some specific field extensions where the binary elliptic curves are defined. The extension should be a composite number for the attack to be useful and efficient. Nevertheless, in cryptography, reputation is everything. So this attack was somehow causing problems in the reputation of binary elliptic curves. So that was in 1988. And then there were other constructions that happened in this period. For instance, N-True, which is once again one of the candidates for the post-quantum contest in the NIST contest, was proposed in 1996. And also in this year, the first ideas of isogeny-based cryptography were presented in a seminar by Kubanes in 1996. And this is another candidate of the PQ contest by NIST. So all of this happened between 1994 and 1998. Then if we enter in this century, pairing-based crypto appeared in the scene. It is interesting because this is based in elliptic curves. It is a bilinear pairing mapping that we were using. And actually, it was the one that was used in the MOV attack that I mentioned in 1993. But in this case, it was used for destructive purposes. And in pairing-based crypto, is used for constructive purposes. So there were several contributions by these Japanese authors, Mitsunari, Sakai, and Kasahara, Sakai, Ogishi, and Kasahara. And this one by Zhu was very, very famous because it was this protocol that he presented using pairings for performing a Diffie-Hellman among three parties and in just one round using binary pairings. And this immediately captured the attention of the cryptographic community. So even though pairing-based crypto is based on elliptic curves, it became a subdiscipline by itself because people were quite excited. And then a myriad of pairing-based protocols appeared in the scene. For instance, there was a very long-standing problem, identity-based encryption that was theoretically proposed by Professor Shamir back in the 80s, and it was elegantly solved using the Bonnet-Franklin construction, which is based on pairing-based, on pairings. Then the short signatures by Bonellin and Shazam, and aggregate signatures that that are very important right now for cryptocurrencies. All of these were proposed between 2000 and 2003. So these years were highly active with the proposal of new protocols. Maybe 10 years after Ju's and the Japanese authors' papers, maybe 1,000 protocols have been proposed in pairing-based crypto. Even a conference that was called pairing conference was running during those years. Also, later in 2006, Groth, Ostrowski, and Sahai proposed a SNARK protocols using pairings. These SNARK protocols were based on pairings, and these protocols now have a high importance for providing anonymity in cryptocurrencies. So now they are very much used in certain cryptocurrencies, such as, for instance, Zcash. So pairings are still alive. Here, I didn't include some attacks that pairings received in 2013 on that were attacking certain classes of pairings, and it seemed that that pairing-based cryptography could be in danger because of these classical attacks, but new parameters were proposed. And now, for instance, if you are familiar with this kind of cryptography, before 2013, we were using Barrett-Honore curves for providing 128 bits of security. And after that, we are using another family of elliptic curves that is called the BLS curves families, and they have a larger prime. We grow from 256 bits to 384 bits, just to prevent the attacks that were discovered during those years. And for now, it seems that we are safe, and we would like to be safe because pairings are really useful for many cryptographic constructions. This is with respect to pairing-based crypto, but then from 2006, isogeny-based crypto was taking off, basically. In 2006, it was an important year because it was proposed a scheme that was somehow similar to Diffie-Hellman for key exchange. It's called the CRS crypto scheme, and it is now known as CRS because of Kovains, Rostovtsev, and Stolgunov, who proposed that independently. On one side was Kovains, and on the other side is Russian co-authors. So that was in 2006. And also in 2006, a hash function was proposed by Charles, Leuter, and Goren. And this shouldn't be here. I'm sorry about this. So these were the constructions that were proposed in 2006. But then isogeny-based crypto received acquired a much more importance with the publication of this protocol, SIDH, in 2011. This was proposed by Luca De Feo and David Yao. And after several years, when the NIST contest started, this SIDH was modified to include a chem mechanism, as it's called. And then this psych crypto scheme was proposed and is now in the NIST contest. And it made it to the third round as an alternate candidate. After the NIST contest was closed, there were several proposals for different Diffie-Hellman kind of protocols. For instance, this protocol CSIDE is famous in the area of isogeny-based crypto because it's the only post-quantum construction that is known that fully emulates the Diffie-Hellman protocol in the sense that there are no interactions and in the sense that you can use static keys for Alice and Bob which is not possible with any of the other post-quantum candidates. There are other developments because this area has been developing very fast. For instance, there is one proposal by Greg Costello that is called BSide that seems to be very promising. And also this signature ski sign that appeared in 2020 in Asia Crypt, and this is very promising because it's the smallest signature in keys that you can find for producing post-quantum signatures. So isogeny-based crypto, the same as in the case of pairing-based crypto, became a subdiscipline by itself, but all of them, you could claim that they belong to a big umbrella that is elliptic curve crypto. The only thing that is that isogeny-based crypto, as opposed to pairing-based crypto and traditional elliptic curve crypto, this branch is post-quantum, offers post-quantum security. It means that it can support attacks from quantum computers. And that's why we have it as one of the candidates for the NIST contest. So this is what we have. And then I would like to mention also the year 2013. As you know, and it was mentioned by Christoph in the last talk, there were these Snowden's revelations of surveillance. And this was like a big hit for the whole cryptographic community, especially the concept of perfect forward security came to the spotlight because we knew now for sure, we were sure that the NSA was, for instance, and other agencies were doing some surveillance for many users, for millions of users. So this was one of the consequences of these Snowden's revelations was that elliptic curve cryptography became viral. Many applications showed up after that. For instance, I would like to emphasize that although elliptic curves were in the TLS protocol beforehand, many years before the Snowden revelations, after these revelations, then it was decided that this was the best way to perform the Diffie-Hellman, the key exchange protocol that we regularly perform in the TLS handshake protocol. That means that, yes, EC Diffie-Hellman is the preferred method for performing this key exchange. Also, this curve to 255.19 was proposed. It was already proposed in the 2005, if I'm not mistaken, by Dan Bernstein. And then it was, you can find it ubiquitously in many applications like SSH, like WhatsApp, like Facebook, you name it. So whenever we have a WhatsApp chat, we are using key exchange using this elliptic curve. Moreover, the cryptocurrencies, Bitcoin, as you may know, it was operating since January 2009, and it uses Koblis curve that is defined in the primes, and so do other cryptocurrencies such as Ethereum, for instance. So elliptic curve became the king of all, or the queen of all the schemes, crypto schemes for public key crypto. And it took a long while. It started in 1985, and it took until 2013, basically. We have been enjoying like 5 years of elliptic curves being the queen of all the crypto schemes, which is interesting because you know, if you see the people that are here in this conference, for instance, Professor Kai Savage, Professor Christoph Parr, you know, back in '98 when the first edition of chess was out there with, because the co-founders were Christoph and Chetin Kaya-Koch. Well, ECC was a very young crypto scheme that has evolved until now that it has become the most important one. But what's the problem that we have? The problem that we have is that the arrival of quantum computers that are coming. So here I have a nice souvenir picture. This is Professor Neil Koblitz, and this is Professor Victor Miller in Mexico in the ECC 2012 workshop. It has been a long, windy, and at times bitter battle against RSA, so that ECC is now the undisputed, most efficient, most effective, and most popular pre-quantum or classical, if you will, public key scheme. What are the main applications of elliptical cryptography? Well, as I have been emphasizing, key exchange, but also digital signatures, right? We have several standards that are based in elliptic curve cryptography. For instance, probably the most popular one is ECDSA. And the security guarantees of elliptical cryptography are based on the elliptic curve discrete log problem. But with the arrival of these large-scale quantum computers, we can, in principle, run this originally theoretical algorithm by Peter Shor in the 1994, which begs the question: how long can we safely use pre-quantum ECC, knowing that the large-scale quantum computers can come, sort of speak anytime? So in the rest of this talk, I will try to address the most important aspects, in my opinion, in order to answer this question, which is the main topic of this talk. So maybe the very first question that one can ask is, what are the chances that ECC may succumb to classical attacks? So forget about quantum attacks. Can we somehow break the hard problem that ECC has, which is the elliptic curve discrete log problem, ECDLP, known as ECDLP? This problem is given an elliptic curve defined over a finite field and 2 points that belong to the abelian group on that elliptic curve, then find an integer x, if one exists, such that x times p, meaning adding p by itself x times, give us q. So the problem is, given p, q, and the elliptic curve, find this x. You know, after more than 36 years of intense cryptanalysis, the conjecture difficulty of breaking ECDLP remains exponential. So there is no better way that we know of to solve this discrete log problem than using Pollar's row algorithm or maybe baby step giant step algorithm. And both of them, they have this complexity square root of n, where n is the group order of the point p. So the number of points that live in this abelian group. And there have been some very minor advances in solving this problem, very, very minor. So basically we can say that this statement is still true 36 years after this cryptanalysis started for a sensitive selection of parameters other than the families that we already know that are produce weak elliptic curves. They are still strong, these elliptic curves. For instance, in the opinion of Professor Michele Mosca from the University of Waterloo, he estimates that at most maybe 1% chance of breaking the ECDLP problem could be maybe 1% chance of breaking it using classical techniques in the next decade. This would be like a pessimistic estimate, right? But in his opinion, that may happen with a 1% chance in the next 10 years, just using classical techniques. But so far, as I will say once more, 36 years of cryptanalysis have produced almost nothing in order to dent the security offered by these elliptic curves. So this is what I would say about what about if ECC can succumb against classical attacks. And then an important point that I would like to make is that we, as I mentioned, we have two main applications of elliptic curve cryptography. One is digital signatures, And the protocols that we have for digital signatures are ECDSA and, for instance, EDDSA, and there are others, but I would like to mention these two. In this case, the threat of the quantum computers, in my opinion, is not as you should not worry that much for this application. Why? Because one can prevent future attacks basically by resigning the message, basically by putting another signature over the signed message. And you can use for that not elliptic curve, because you are you have these doubts that maybe quantum computers may arrive. So we should use other post-quantum schemes. Any post-quantum digital scheme of your preference can be used for this sort of oversigning of resigning of a message that has been already signed using elliptic curve crypto. So there is a problem here, but mainly the main problem is to get prepared for the change. But I would say that our signatures that we are producing right now can be protected effectively. On the other hand, for the second application of elliptic curves, the key exchange protocols like ECD-Hellman, ECDH, here we are in problems. And this was one of the consequences of the Snowden's revelations. We are subject in this case to the so-called harvest and decrypt later attacks. So basically, an opponent can harvest all the communications that he cannot break right now, or she cannot break right now, but when the quantum computers arrive, then he can use Shor's algorithm, break the Diffie-Hellman key exchange protocol that occurred back 10 years before, maybe, and then discover all the secrets, because this key exchange, this shared secret is used for encryption using some sort of transformation to that shared secret. Then we use it later for instance, an AES secret key. So this is a major problem, and in particular, one problem that has captured the attention of the community is because it's one of the most sensible targets, is long-term root CA certificates, because these certificates are meant to last for decades in many cases. So this would be something to be worried about. And so this is something that you should take into consideration. And this is true not only for elliptic curve, but also for other kinds of digital signatures, classical digital signatures or key exchange protocols. So my next question would be, how large must be a quantum computer in order to break ECC? So the current quantum computers that we have right now, they have less than 100 qubits. For instance, this famous construction by Google that proved quantum supremacy maybe a year ago has a bit more than 50 qubits. So all the quantum computers that we know of, except if you don't count the D-Wave quantum computers, they have less than 100 qubits. However, due to the error rate per gate, those qubits can operate no more than 20 quantum gates in a row. This is important because when you are building this quantum circuit, you have this concept of the depth of the circuit, and the more depth you have, the more error correction you must do, because some of the qubits may decay, and then they can lose the information that they have. So this is a problem that we have in the current state of the art or in the state of the technology of quantum computers. A Shor's algorithm, just for you to know, requires theoretically something like 2,000 qubits to break practical instantiation of elliptic curves. But provided that these qubits can operate between 100 million and 1 billion quantum gates in a row. So we are a long way from where we are here in the first bullet to what is required in the second bullet for breaking ACC for a practical instantiations of that crypto scheme. And there is always a trade-off between the space cost. This means the total number of physical qubits that the quantum computer will have, and the time cost proportional to the depth of the quantum circuit. So in many occasions, we say that we need to multiply the depth times the width of the quantum circuit to know what is the actual cost of that quantum artifact. Just summarizing, there is a general consensus that a large-scale quantum computer should be equipped with more than 10 million qubits in order to break practical instances of ECC in one day. Why you want to break it in one day? Well, because the Shor's algorithm is so powerful. So if you give to Shor's algorithm a powerful quantum computer, it will do it in less than an hour, maybe. But you would need this many qubits to do it. So there is a long way in order to have this kind of quantum computers. My next question is, what are the main challenges preventing the constructions of larger quantum computers? Why we cannot go from 50-something qubits to 10 million qubits? Well, there are many challenges that still must be solved. For example, these quantum computers, they work in extremely low temperatures at the moment, although there have been some advances in that regard. But the ones that we have right now, they work almost at 0 Kelvin degrees, a bit above. And this is a big problem for constructing these quantum computers. We obviously need to find ways to increase the number of physical qubits so that we have that this scales well. At the moment, it's not doing it. And also, it is important to reduce the error rate per gate that we are having right now. We are probably in 10 to the minus 3, meaning that for each qubit, you need at least 1,000 qubits that perform the error correcting of the degradation of these qubits, and this needs to be improved to 10 to the minus 5 in the future, which right now we don't have it. So this is why this is some of the reasons why we don't have larger quantum computers right now. All things considered, when will large-scale quantum computers be ready for breaking ECC? And here it depends who you ask. This is the most repeated question: when these quantum computers will be able to break ECC. And you can have pessimistic people, optimistic people, negationist people that say that will never happen. But we believe that, for instance, see this line of reasoning. Assume a sort of Moore's law for the construction of larger quantum computers. And that means that about 16, that every 18 months, we double the number of qubits. Let's assume that way to think. So we would need about 16 doublings, Moore law's doublings, in order to get from say 64 qubits to 2 to the 20 qubits. And 16 doublings will means this means that basically if this assumption is true, which is a wild assumption, but is a way to reason this problem, then you would say that maybe in the year 2045 we will have something that will hurt ECC badly, if you think this way. And there are other people that do other analysis, and they say that yes, maybe between 20 years, we have maybe a good percentage of chance of having a large-scale quantum computer. For instance, Professor Michele Mosca, he is estimating a probability of 20% that a quantum computer will show up in the next 10 years with these capabilities. This is This is one way to see it. But of course, as I mentioned, there are other more optimistic points of view than 2045. So have a look on this slide. This was presented in the RAM session of Latin Crypt back in 2017 in La Habana, Cuba. And this is a bet that we claim that this is the largest quantum computing bet ever. So it's a record in that sense. The two people who are betting is Dan Bernstein and myself. And these are the rules of the bet. The price is 2048 US dollars, so $1 per bit, because we are talking about the factorization of RSA 2048, which is, by the way, more difficult than breaking ECC, as we will see in the next slide. In order for Dan to win, this must be publicly announced, not secretly announced. The factor should be available, and it should be clear that the attack was made using a quantum computer rather than using classical techniques, and before the deadline. Otherwise, I will win. And the deadline is the ROM session of Latin Crypt 2033. So I still have how many years? 12 years to win this bet or to lose it. Whoever loses this bet will receive from the winner a nice dinner. So let's see what happens from here to Latin Crypt 2033. You are most welcome to come to that edition of Latin Crypt. Anyway, my next question. Could funding for quantum computing decline in the near future because people get impatient and they have invested a lot of money, fortunes, I would say, especially in Europe, but also in China, Canada, United States? I think that is highly unlikely. Actually, there is a strong funding from different agencies and countries for achieving the quest of building quantum computers. So it seems like this is going up, not going down. So people are really excited about this quest, and they are trying to get this quantum computer. So I think that the funding will still be available for many years. But then why should we worry now about the end of ECC if so many things must happen? Well, among other reasons, you should consider that it takes a lot of time to transition from one technology to another one. So as I was saying, digital signatures is not a big problem compared to key exchange, but we need to prepare for the transition. And it takes years, if not decades, in some cases, to transform from one technology to the other. Just take into consideration, for instance, the case of DES and AES, that still we are using DES after more than 20 years that AES was proclaimed as the new standard for encryption. And the same happened, for instance, with SHA-1, that is still used somewhere there. So we need to act right now. This is the first argument. Second one, there is some chance that quantum computers might be ready by the next 10 years. Who knows? As I said, according to Professor Michele Mosca, there is a 20% chance in his estimations that this might happen. Also, long-term secrets must be protected now because they are being harvested now. So they are subject to these harvests and decrypt later attacks. So this means that for some top secrets, it might already be late in the sense that they have been already harvested. And the people, the attackers, as we call it, is just waiting for the quantum computer to show up in order to open up these top secrets. Which one will be broken first, RSA or ECC? ECC. If this happens, if the quantum computers arrive, ECC will be the first to be broken. And this is the most intuitive reason is because of the smaller key sizes, which is the most important feature of ECC pre-quantum. Well, this is the main problem when you are attacking ECC, that it has a smaller keys, like 1 order of magnitude smaller than RSA, and therefore you require less qubits in order to break ECC. So ECC will will perish first. So that gives me a little bit more of hope of my bet, because when I see that ECC has been is broken, then I will be in problems, because RSA will be next. More questions. Could we expect that ECC will still be used after the arrival of large-scale quantum computers? Yes. Yes. Even if quantum computers arrive tomorrow, we will still be using ECC. Why? Well, there are several reasons to to be optimistic on this sense. One of them is that the quantum computers are very expensive. So even if large-scale quantum computer arrive in 1 year, let's say, during the first years after their arrival, there will be a limited number of them. So we will have some buffer time to know that that our days are counted. But yes, that would be one reason. And then for some time, there will be scenarios where the security provided by ECC will be acceptable. For many scenarios, ECC will still provide security, even in the presence of large-scale quantum computers. And also, there is one robust line of research that is calling for hybrid crypto systems, where you have a crypto system that combines classical cryptography, meaning ECC basically, combined with your preferred post-quantum crypto scheme. So these hybrid crypto systems probably is the way to go in order to perform the transition from classical to quantum post-quantum cryptography. And for instance, you can check in the references in the internet. Google and Cloudflare have already made real-world experiments on this line of research, meaning that they are using a TLS that use a hybrid crypto system, and they have their experiment considered millions of connections, TLS connections. And their main idea of their experiment was to determine which post-quantum candidate was the most well-suited for doing these hybrid crypto systems with ECC. And apparently, the experiments conclude that the best ones are the lattice, at least in terms of performance, and for most of the scenarios, lattice-based candidates appear to be the most effective and most efficient for this. Well, just to finish this, well, you may wonder where all this started, and it was this gentleman, Richard Feynman, who published a very, very famous, one of the most famous papers ever, simulating physics with computers. And he said this, and I am not happy with all the analysis that go with just the classical theory, because nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. When Feynman made this remark, he already knew that he had cancer, and he passed away a few years after this paper. And this is what it took us all the way here. The secure. Gracias. Thank you. Bad pronunciation, right?
Thank you very much. It's a great pronunciation. Gracias.
Much better than mine.
Thank you for the excellent talk. I think there's a single question. Can you see the question?
Just one, yes.
Yes, could you?
Rene is, hi Rene, he is asking, I don't know if you can see the question from my screen.
Yes.
Okay. Do you think that predictions about quantum horizon are influenced who receive funding? Yeah, well, this is a big question, Rene. Yeah, you know, all these research groups are receiving very large amounts of money for their research. And maybe some people are, you could say that maybe some of them are over-optimistic. But I would say that many of them are just honestly given us their best opinion about what's going to happen, and really is a wide spectrum, right? From the negationist people, from the highly optimistic people. But yeah, this is a difficult question, Rene. And then
there's a nice one. Yeah.
Say it again.
There's a nice question. Yeah, can existing ECC hardware be reused for supporting post-quantum secure algorithms like SIDH?
Can existing ECC? Oh yeah, this is a nice question. Yeah, for instance, talking about these hybrid schemes that I was mentioning. So the idea was, well, if you already have hardware, if you have already devoted your time for designing a very nice hardware accelerator for ECC, can we reuse most of its components for combining that with SIDH or SIG, which would be the candidate, the official candidate? And my answer is yes, definitely. It is a very natural idea. The thing is that, in order to be fair, SIG is more or less one order of magnitude slower than the fastest lattice-based candidates. So even if you have the disadvantage of combining the ECC hardware accelerator with SIG, even in that case, you could say that lattice-based candidates are almost unbeatable in that sense, in the sense of performance, at least.
And it all depends on the implementation, right? I mean, in the end, it's all about, arithmetic, modular arithmetic. So it depends how it was implemented.
Absolutely, Erdik, absolutely. Yeah. It is, yeah, you need to check case by case, I think.
Case by case, yeah.
And we have a very beautiful line of research there, Erdik, if you ask me.
Yeah.
Yeah, another question. Although quantum computers are expensive, I would not recommend using a breakable cryptographic algorithm. Yeah. Like, would be able to have such computers while the vast majority. Yes, Anes, I completely agree with you. The first ones to have a quantum computer most probably are going to be the agencies. And this is a problem, as we have seen, because of the surveillance that we have. Yes, so the governments are doing a lot of investment on this, United States, China, and the European community also. So I agree with you, Anas. No, Latif.
One last question, yeah.
Yes, thank you, Latif, for the question, but the answer is no. No. You cannot increase ECC because it would be completely broken. They are talking about minutes if Shor's algorithm is provided with a large scale quantum computer, less than an hour to break ECC. So there is no way to rescue ECC if the quantum computers arrive. It would be dead. They can still be used in certain contexts, assuming that there are not many quantum computers at the beginning, but it will be broken. Yes, Tashin is asking me, do you believe that there will be an improved Shor's algorithm soon? The thing is, Tashin, that Shor's algorithm is already wonderful as it is. The problem that it has is that we don't have a quantum computer. So this is a funny situation, right? Because, yeah, what we don't have is the hardware, but we already have the algorithm waiting for the hardware. So this is the situation that we have. Yes.
Yep.
Sasid is asking me, we are worried about the arrival of, but we haven't made it to quantum safe systems yet. What is the reason? Well, it takes a lot of time because it's easy to make mistakes. Imagine that you decide, that NIST decides to standardize one algorithm, and 1 year later, someone discovers a huge attack against that candidate. Then it would be a terrible waste of time, of years of transitions. So we need to be very careful. It takes a lot of time just to take the decision of changing from one cryptography, in this case elliptical cryptography, to one of the post-quantum candidates. So what NIST is is probably going to do, at least the rumors run that way, is that NIST is going to select not one, but 2, 3, maybe more candidates, post-quantum candidates, so that people have the options in case that one of them gets broken. Yeah.
Okay, I guess all the questions are answered. Thank you for the wonderful talk again.
Thank you, Erding.
Yeah, we should move on to the next speaker. Thanks for your time. Our next speaker is Aydın Aysu. Let me first introduce Aydın Aysu. Dr. Aysu is currently an assistant professor at the Electrical and Computer Engineering Department of North Carolina State University, where he leads Hector, Hardware Cybersecurity Research Lab. He got his master's degree from Sabancı University in Istanbul, Turkey, and his PhD degree from Virginia Tech. And before joining NC State, he was a postdoctoral researcher at the University of Texas at Austin. His interests are broadly on hardware security research and cybersecurity education. He has won the 2019 NC State Faculty Development Award, 2019 NSF Research Initiative Award, the 2020 Bennett Faculty Award, and the 2020 NSF Career Award. His papers have been nominated for the Best Paper Award at 2018 and 2019 at IEEE host conferences, and have won the Best Paper Award at 2019 VLSI, and 2020 DATE conferences. He's an IEEE senior member and has an ERDOS number of 3. Aydın, the floor is yours.
Hi, everyone. First of all, are you able to hear me?
Yes.
Oh, that's a good start. So my internet is a little bit sketchy today, but I'll do my best and hopefully all will go well. All right. So I hope you're also able to see my laser pointer. Obvious. Oh, okay, great. Great, awesome. Welcome, everyone, and thanks for staying until the bitter end. I'll try to make your time worth. So in this talk, I'll be trying to identify the trends that I see for the future of crypto, and specifically about the physical side channel analysis. And I'll try to make some projections for the next decade. I will be talking mostly about other people's work, but however, I will occasionally identify how my works or my published papers do fit into these kind of trends, which has started now. And for those works, I would like to thank my students and my postdoctoral researcher. And I also acknowledge our sponsors, which are Semiconductor Research Corporation, the National Science Foundation, and Center for Advanced Electronics through Machine Learning. I'll talk about side channel analysis, which essentially aims extracting keys from cryptographic systems. First of all, before we even discuss side channel analysis, so we should first think about the primary channel. So the primary channel is typically doing a mathematical attack on cryptographic circuits or cryptographic systems. And these mathematical attacks are proven difficult, at least for most of the time and for most technologies. So side channels, therefore, has become a very important and dangerous attack. And side channel analysis essentially tries to extract some implementation correlation rather than mathematical correlation to break a system. This can be things like a power consumption, electromagnetic radiation, execution times, and all of these occur because at the end of the day, a cryptographic algorithm has to execute in hardware. And when it executes in hardware, there are these kinds of leakages. And this analysis has two components. The first one is attacks, and the second one is defenses. So, and the ultimate goal of the defenses is to make sure that there is no extra advantage gained through side channel leakage. Or in other words, the side channel security is equal to the primary channel. Before I start discussing about the future, first let me give a brief overview of the history. So there are two kinds of, at a high level, two kinds of side channel leakages. The first one is through physical sources such as power, EM, acoustic, photonic, thermal, and so on. And there are digital sources such as execution time, which I would consider as a digital side channel leakage. There are microarchitectural attacks that are being very popular right now, and there are memory patterns, things like memory cache accesses, which have some correlations to the secret keys. However, today I'll be talking about the physical side channel analysis. So this became apparent, at least to the public, in Crypto 99 through this very famous paper that's called Differential Power Analysis, or DPA in short, where Kosher et al. Has shown that there are obvious leakages in the power consumption of a circuit, and using those leakages, we can actually extract secret keys. The figure here at the top shows that the shift operation amount can be identified from power consumption. And if this shift amount depends on the secret key, then there is a certain leakage. The figure at the bottom is also from the same paper, and that shows that if the adversary obtains multiple readings, power readings of a fixed key, then it can run a statistical analysis. And there are some statistical features that can identify correct keys, shown here in the bottom, from incorrect keys, right? There are certain peaks here that shows a certain statistical correlation. So these kinds of attacks, therefore, are very they are very important, and we have seen many of such works in the 2 decades from '99. I'll be talking about power-based or EM-based side channel analysis, and these are very popular because they don't manifest themselves because of a side channel, because of a bad implementation per se, but they occur because of the fundamental property of CMOS, right? We know that part of the power consumption of a CMOS circuit is dynamic power, and that itself depends on the data transitions, right? If there's a 0 to 1 switch, or there's a 1 to 0 switch, then there may be certain characteristics, right? So, and because of this, the CMOS circuits leak information about the data that they process. And if those data depends on the key, then there is an inherent fundamental correlation. And these attacks are, relatively speaking, they are much more efficient, much lower cost compared to optical side channel analysis, and they are more precise than thermal. All right, so talking about defenses. So the paper here that I show has appeared at Chess 99, that is 1999. Chess, by the way, and is the most well-known and the most and the highly and the top-ranked conference in hardware security. So at Chess 99, a paper appeared that proposed a duplication method. And the idea here is that to have all intermediate computations be splitted to randomized and fresh shares, so that even if there is a leakage, that leakage itself, it's statistically independent of the secret key. This is done in such a way that the input-output characteristics are still the same, right? You have the same input, the same output, but all intermediate computations are randomized, similar to secure multi-party computation. This is Chess 1999. 1 year later, a similar paper that appeared that is doing this technique to what we call AES today. And this technique, the application, is nowadays called as masking. And fast forwarding 2 decades of research, this is the papers from Chess 19. So that's after 20 years. And we see sessions that are dedicated to masking AES. So we have been masking AES over and over again for over 2 decades. And there are still many papers that appear. So that is important. We should still continue masking AES, and probably by this rate, by Chess 29, we will have a full day of AES masking. And kind of 2019 is kind of the soft threshold that I use to distinguish the past from the future of physical side channel analysis. So I will be talking about the research that I would like to see more of from 2019 to 2029. And perhaps when we come back to this talk by CHES 29, we will then start, we can compare and see if those papers actually became dominant, or are we still masking a yes? So we can have like a comparison like that. So I will be talking about 3 directions today that has started and that I hope to dominate the research of physical side channel analysis. And these 3 directions are new applications, new means, and new devices. And I'll go through one at a time. So first and foremost, new applications. By new applications, I do not mean masking or doing side channel attacks on post-quantum crypto or lightweight crypto or other kinds of crypto. That is also important, but we should be bolder than that. By new applications, I mean new, fundamentally different applications. And I would argue that there are some other applications that also need cryptographic level of security that are beyond crypto. So the first question is, are physical side channels limited to crypto? And the answer is obviously no. And I'll make the case for side channel analysis for AI or for machine learning in general. There are all these edge AI chips from all these famous companies. They perform some AI or neural network or machine learning classification tasks in the field. And in fact, if you look at the market projections, the edge AI is dominating the market. So right now, like there are about 750 million devices, and by 2024, there will be 1.6 billion of those devices. And these devices will execute, again, some inference tasks. Here, the important thing is not cryptographic keys, right? You don't have crypto keys in ML, but you have machine learning models, which are indeed valuable IPs. Today, it's estimated that a model developing a model can cost for more than $10 million, right? So this is true because the training data is expensive, and training process itself, typically with GPU farms, are also very expensive. And therefore, the trained model parameters can be considered as long-term secrets. Here is the threat model I have, which is very similar to, in crypto circuits. So we have 2 phases. We have a training phase and an inference phase. So during the training phase, we assume that the system is trusted. So we can train on the cloud, we can feed in inputs and labels and train a model. And once the model is achieved, then the model is then dumped into the edge device. And then the edge device will perform these classification or regression tasks. And there, an adversary can either fire or observe inputs, look at the corresponding outputs, collect some power measurements or EM measurements, and can run a side channel attack, right? So that's the threat model. And this actually has happened. So at Usenix 19, there was a paper, the first paper that published an attack on stealing models from a low-cost microcontroller. And here, the figure at the top, you'll see that at the high level, so the weights, which are so this is done on a neural network. So there are weights and biases that define the model parameters. First of all, we can actually see those multiplications with neural network weights. And here at the end, you can also identify where the activation function, which is the nonlinear computation in neural networks, are processed. And moreover, the same paper also showed that by obtaining sufficiently many measurements, the adversary can identify correct weights from wrong weights. So here in this work, it's shown that about 10,000 measurements are needed to make this statistical differentiation. And this is just based on simple Pearson correlation, right? So we have, about 10,000 measurement is sufficient to break into a circuit and to steal its model. We did something similar. We did this on a hardware engine that performs parallel computations, highly parallel. And we have shown that, well, first of all, you can still identify the high-level computations. In this case, we are attacking a three-layer MLP, and first we can identify all these independent players. And we can also run these well-known differential power analysis attacks. So here, the green plot shown shows the correlation of the correct guess, which has a peak. So it actually crosses some certain high confidence bounds so that this can be extracted. And the figure at the top here shows that we need about 40,000 measurements to break into this circuit. This is very well known as now, and this is actually similar to attacking cryptographic circuits. So now that we all agree on that these are breakable, so what are the defenses? Are we going to follow the same path of masking machine learning for decades, or do we need to do a more structured approach? That is still unanswered. But we had a few showcases of how do we transform the techniques that have been developed in crypto research for 2 decades and how we can map them to machine learning computations. And machine learning computations are very different than crypto computations. So in our first paper, we've shown that by using a combination of masking and hiding, which essentially aims power balanced circuits, we can achieve a moderate security low area solution. This innovative combination is needed because there is a sign arithmetic leakage in crypto, in machine learning circuits. In our next work in Boomanet, which is recently published as well, we have shown that a Boolean masking can be done. So Boolean masking idea here is that you can reformulate all computations in a machine learning classifier as a sequence of XOR gates and AND gates, and then use masking operations at the gate level. You can, masking an AND gate is known, and XOR gates are known, so you can apply this combination and achieve a high security design at a high cost. So these are just 2 case studies, and this is the only 2 works that have appeared. So so we will see in the future, and I speculate that there will be many more attacks and many more defenses that will fix those leakages. And I would argue here for a more structured solution, and hopefully we can get there in less than 2 decades. The second question I ask is related to the new means, and which is, do we need physical access to run physical side channel attacks? The answer is no. We can do side channel attacks remotely. And the first paper has appeared at date 18, which is showing a remote side channel attack on an FPGA device that serves 2 users doing 2 different applications. And the idea here is that one user, which is the victim, is performing AES computations, and the other user has configured a sensor purely with RTL that can measure the power consumption on this FPGA. And by reading remotely the values of these sensors, we can actually run an attack on an AES and do the DPA. The sensor here is based on an time to digital converter that buffers a certain number of ones. And if AES is using some power, so the available power will be lower to this sensor, or because of power fluctuations, the number of ones that are captured in these latches can change. And based on that, we can infer the power measurement, the power consumption of the circuit. And if we can infer that, then we can run an attack on AES. The next paper took this one step ahead and shows that we don't need 2 users on the same FPGAs. But if 2 users are on 2 distinct FPGAs that are connected through the same power supply unit inside a rack, there is still a power leakage. The paper is not doing a side channel attack, but it is doing a covert channel attack, so that one FPGA is sending information to the other through power consumption. And here the FPGAs are using ring oscillators to, first of all, to stress the power consumption on the power supply unit, so that the the power consumed by the other FPGA actually has detectable patterns or detectable fluctuations. As I said, this is just a covert side channel, but I think in the future, we'll see side channel attacks as well on these kinds of systems that use heterogeneous computations, heterogeneous platforms, which are connected through the same power supply unit. So we need to invest and we need to take a look at how that domain is actually being explored. Here's another paper from this year's Oakland S&P. So this is doing an attack, a remote side channel attack on an x86 on an Intel device by reading the values of the Intel's RAPL units. So RAPL stands for the running average power limit, which gives a very coarse-grained access to a user so that the user can snoop on the power consumption and try to optimize their software or whatever. This interface can again be abused by an adversary remotely and do remotely read the software that runs on an Intel x86 and can again, using those measurements, the adversary can run an attack. The paper shows, first of all, different instructions can be identified. The red line here is for a move instruction and the blue line here is for a CL flush. So these two instructions have two different power consumption. And if you again collect sufficiently many measurements, you can identify that. Moreover, the paper also shows that if you pick a specific instruction, say the move instruction, then there is a correlation between the power consumed or the energy consumed and the Hamming weights of that move operation. They even show that different cache hits, different cache line hits in the microarchitecture can be identified based on power consumption. And all of these, when combined, leads to reverse engineering a software and run side channel attacks to extract cryptographic keys. And the last paper that I'll be highlighting here is published at CCS. So this is a very interesting paper because it shows that essentially the vulnerability in one part of the logic can be broadcasted in another part. So they showed that here in a particular device, the RF front end, the radio, and the digital logic shares the same substrate. So the noise on the digital logic gets broadcasted through the radio signals. And because it is broadcasted over radio signals, the vulnerabilities in digital logic, the power consumption vulnerabilities, can actually be measured by a remote adversary. So here they showed that when the transmission is on without an AES, without any operation, versus when a transmission is on with an AES being computed on the digital logic, there are distinct features. And they then showed that the AES computations and the secret key dependent power can be extracted by looking at this RF front-end signals. So that is also something that is very important. Therefore, I would assume that there are all these kinds of the works that we will see over and over again in the next decade. And the last trend that I want to identify and highlight is related to the new devices. So are physical side channels limited to smart cards? When this side channel work has appeared, it had an immediate impact on smart cards or low-end devices. But we have seen recently that these attacks do scale to more complicated and much more complex platforms. This actually didn't start in 2019. This is something that is older. So the paper on the left is from K. Leuven, which showed that an EM probe placed on a relatively complicated microcontroller that operates at 1 gigahertz, so this is ARM Cortex-A8, can be used to run an EM-based side channel attack. The patterns here that you see, they are the AES rounds. And once you obtain these AES rounds and then focus on a particular round, you can again see these leakages. So the black line here is the correlation of the correct guess, and it leaks with about 2,000 to 3,000 measurements. Likewise, the group from Northeastern has published that NVIDIA GPUs are also vulnerable to side channel attacks. They have put a resistor in series between the main power line and the GPU, and they showed that once they obtain these power readings, they can again run a correlation attack, and that's the correlation, as you can see here at the bottom, after obtaining about 50,000 traces or so, there is the adversary can get this key. So GPUs are attackable. ARM Cortex-A8 is attackable. And most recently, we have seen, this is from UseLeaks 21, we have seen that Google's Titan security key is also vulnerable. But the researchers have shown here is they took this device in the middle. They have chemically etched the unit that performs crypto operations, and then they put an EM probe on top of it. And after some black magic and some post-processing, they have shown that the elliptic curve computations, such as doubling and addition and so on, can be identified, and the secret keys can be extracted. So this device is also vulnerable. Likewise, Chess 21, there is a new paper that has appeared from Moradi's group. And this work has shown that the iPhone is also vulnerable to EM-based side channel attack. And this is placing the EM probe on a hardware accelerator in iPhones that performs the AES computations. And you need more measurements. So you need about 250 million measurements in this case. But again, the hardware AES unit inside an ARM SoC is also attackable. We did something similar. This is not published, so please take it with a grain of salt. We have shown that, so this work has shown that iPhone 4 is vulnerable to this attack. We did an attack on a newer iPhone, much newer iPhone, and we looked at the scan of the iPhone circuit, and we placed EM probes on the big core. Then we shown that the EM leakages actually do leak. So there is a vulnerability when you put the probes there, and you can actually identify when the core is activated versus it's inactivated. And if you look at it more closely, you can identify different computations, different instructions, and even different data. So we have observed that the one on the left is the T-table implementation, and the one on the right is the ARM CE implementation running on the big core. This is similar to similar to Apple's crypto library, and we can identify the t-test leakages that appear in both cases, and that even those leakages, there are intermediate correlations and intermediate variables that do leak information through the EM. So input correlations, output correlations, and secret keys can be identified by getting about 50 million traces. So to conclude my talk, since 1999 to 2019, for 2 decades, we have seen a lot of works, thousands of papers on physical side channel analysis. This is a real threat. There are hundreds of millions of devices that are using defenses exclusively against physical side channel analysis. We have masked the heck out of AES. We have shown a lot of work, but I don't think that's really the future. We will still keep seeing such papers, such sessions, but I think there are newer applications, newer means, and newer devices. There are newer directions that I think will dominate this line of research. And I just identified 3 of those, and these are not mutually exclusive. So they can be a combination of these 3 as well. So on the new application side, I think we should start thinking about side channels beyond crypto. And the defenses, we don't have that much time to develop and deploy defenses. It is much harder to do it for ML because we don't have standards in ML. But there must be a significant amount of research and funding that goes into this line of work. And the ML is just one application. So, and something very important is to see what newer applications will appear in the next decade and how do we protect those against physical side channel analysis. On the new means side, we know that now physical leakage can be extracted remotely through various means. And we don't know what it means for the whole system. If we are not going to fix the side channel leakage, then perhaps we should fix the way it's manifested at the RF front end. What does it mean for RF engineers? So can we have an obfuscator unit that obfuscates the noise or decorrelates the noise on RF so that the AES leakage, AES vulnerabilities on the digital core is no longer manifested? There are many other directions, right? So this has significant impact on the whole system design. And for the new devices, so we know that now there are many works and that physical side channels are not limited to simple IoT devices. So what's the next target? So that is the conclusions that I have for today. Thanks very much for your time. I also thank you guys for inviting me to this talk and be part of this distinguished panel. And I'll be happy to answer some of the questions.
All right. Thank you very much, Aydın. That was a really interesting and insightful talk, and we learned a lot. So we may have, some time for question. So do you see the Q&A box?
Yes.
Like two questions. I mean, if you can read them, I mean, maybe, if you want to answer them. Yeah.
Sure, I would like to answer them if we have time. So for secure memory on slide 11. Oh, that's great, thanks. So for secure memory on slide 11, please share some details about the security requirements of the memory. Well, so I do not mean that we are designing a secure memory, but so what I suggest by that is that we can use existing secure memory solutions to store the weights and bias parameters of a neural network so that memory may not be extracted. So the memory doesn't have any leakage, but I'm not claiming that that problem is solved. So I'm just claiming that we do not look at that problem. So I think there are all these attacks, such as the cold memory attacks or the cold boot attacks, which can again apply to machine learning model stealing, right? So that may be for perhaps a very good attack vector. The second question is, thanks a lot for a great overview about recent side channel attacks. The question is, do you know about any audio-based side channels that have been used? There are some papers on audio-based side channels and audio-based covert channels. That is very important for air-gapped circuits or air-gapped networks, right? So there are some devices that are not allowed to connect to the internet. But if you have a microphone that sits right next to it, and if you turn on that microphone, then maybe you can leak information. There is I believe, a recent paper that appeared at Oakland S&P that is doing this kind of work. So you may want to check that. There is another, let me read the question first. For very short-range interchip communications, there is an approach which uses terahertz wireless communications to reach ultra-high data rates. Do you think that this approach is even weaker against attacks? Well, I'm not an RF engineer. During my undergrad at Sabancı, I've even skipped that RF class because I thought it was a very hard topic to understand. I would refer this question to the RF experts in the chat. I'm sure that with different communication technologies, there will be different challenges that we have to look at. For ML accelerators, there are some companies like Cerebras that have built wafer scale chips, introducing a new ISA. Can such architectures provide hard? No. Parallel computation never eliminates leakage. So it increases the noise, but the correlation is still there. So it's, at the end of the day, it's a matter of signal to noise ratio. If you have multiple cores doing multiple operations, and if you want to target one of those cores, you can still do it. And especially with these multi-GPU or multi-core devices, if you have a strong EM probe, you can isolate the area where you collect your measurements. So you don't really care about what happens on 800 cores, but only few of those. And you can run an attack like that. So I can say that edge TPUs that have all these cores, they would still be vulnerable to EM or power-based side channel attacks. There is another question that says, how do you see such attacks developing for post-CMOS? That's a great question. So newer memories, Swarup Ghosh from UPenn is working on how in-memory computing and in-memory accelerators leak side channels. So there are some people that are looking into these newer memories, perhaps not in the context of AI ML, but in crypto, in AES. Post-CMOS, I think the leakage will be there. So it depends on which post-CMOS technology you are thinking of, but there will be a vulnerability, either power, EM, or some other, as long as we compute on secret keys, and as long as the device uses some amount of power. There is another question. This is not a question, okay. So there is also a link. Well, I'm not sure if I'm supposed to read anything beyond any questions, but there are all these great works that are out there.
Yeah. Aydın Hocam, thank you very much. Thank you very much. That's, again, I mean, taking your time and then answering all the questions patiently. And thank you very much. I guess we came to the end, and I am supposed to give some concluding remarks. And I guess it was a nice, event and activity, and I myself enjoyed it, and I learned a lot. And of course, I have to thank all the the speakers, and they just participate. They joined this event from different countries. I think that's kind of a nice event, right? Because 4 different countries, and the speakers are joining this event and they are contributing. And I would like to thank each one of them. Ingrid, thank you very much. I mean, it's an honor to have you here. Thomas Eisenbart, you are not here, you have to leave, and I really thank you very much for your great talk. Patrick Chamon, Patrick, thank you very much. I mean, you are joining from Massachusetts, Worcester. Thank you very much. It was really insightful talk. And Christoph, in fact, Christoph was the one of the ideas are coming from him to start this event. And thank you very much, Christoph. You are not here, but the video is going to be available in YouTube, so you can see how I thank you. And Francisco, thank you very much. Joining from Mexico City, nice. I really enjoy Mexico City when I was there. I mean, thank you very much. It was a really nice talk. I really enjoyed, and I learned a lot. Thank you very much. And finally, yes, Francisco, thank you very much. Yeah, I hope we can, see each other very soon physically. We can arrange a similar, thing. Aydın, thank you very much. So it's really nice to have you here. So I really thank all the speakers, and I want to thank all the technical staff here, and they work really, work diligently here, to make this happen. And I think we, did it without any hitch, any mistake. Thank you very much, for everything. It was a really good effort. And also, I just want to thank all the participants, joining from different countries, and there are still like more than, like 100 people sticking around and, contributing to the success of this event with the wonderful questions. And some of them are comments, not questions. And thank you very much, all the participants. And, I just want to thank our president, Sabancı University, supporting us, giving the idea to make this event happen. And make sure that the cryptography is important. So we discuss some important stuff here. So Sabancı University is basically, we are having graduate, programs here on cybersecurity. We have some PhD students here. We have projects here. We have, programs for professionals. Thank you very much. And I just want to say you have a great weekend already. And so bye now.